Hi. That actually, yeah, so I don't travel much. Okay. Also,
Welcome everyone. Let's get started. This is welcome to all of you to this Statphys Kolkata 12th conference. This is a 12th conference in a series of conference which started from 1992, the first one. And since then, every 2-3 years, few institutes in Kolkata, they get together to organize this event. Last time, because of pandemic, it was fully online, and this time we are back again in the usual offline mode. Okay, so just few announcements. In your registration kit, you will find a water bottle given. So we are avoiding use of plastic. So there would be water dispensers kept outside where you can fill it in. What else? For the people who are presenting posters, you can please upload your posters during the lunchtime. Okay, the poster boards are there with your poster number printed on it. You can upload those posters online. The first session will start in just a couple of minutes. The talks are of 30 minutes and 15 minutes duration, and I leave it up to the session chair to conduct the timings very strictly. But in general, it is 25 plus 5 and 12 plus 3 for these two types of talks. So, yeah, so, okay, so, yeah, I don't have to say much more. So, we get started in, what time is it? Yeah, 3-4 minutes about. If every speaker of the first session have not uploaded your talk yet, please do so. If you are using your own laptop, then that's a different thing. Okay? Okay, thank you very much.
What I said, you need a character in the custody of state. By another, how will you get that? Yeah.
Our session will start now. It will be chaired by Abhishek Bhatt from ICDS.
Okay, good morning, everyone. Okay, so my name is Abhishek Bhatt, and I can say in the first session, which has four talks. So I've been, as the organizers have said, we have to keep to the timings. I request all the speakers to be very particular about time. So the first talk is by Sriram Ramaswamy, and we will talk about non-reciprocal magnets.
Can you hear me? Thanks. Many thanks for inviting me to this conference. I was at the first Statphys Kolkata conference. It's quite a exciting affair. End of 91, early 92. In a very interesting setting. I think we should try to repeat that conference at that venue one more time. Those of you who were there know what I mean. Anyway, thank you very much for the invitation. It's great to be here. I'm going to talk about something that's not exactly active matter, but arguably has something to do with it. Spin systems with non-reciprocal. Sound is on. So I'll start by telling you what I mean by non-reciprocal. I'll then discuss two examples and two different kinds of non-reciprocals, two different kinds of non-reciprocity. So first of all, as you know, although interaction is governed by a potential energy or something are strictly reciprocal, social interactions are most certainly not constrained by any requirement of reciprocality in ways that can be quite unpleasant. Someone can like someone else who can dislike them. Even the interactions that lead to blocking in some kind of systems can actually be as weird as one thing trying to pursue another to eat it and the other trying to escape. That can give rise to a ferromagnetic alignment of their orientations. More generally, any interaction that involves signaling is naturally non-reciprocal in nature. As I said, if you have an effective energy function governing your system, then such non-reciprocality is ruled out. The topic has sort of caught fire recently, and there's been a lot of work from various groups, notably Vincenzo Vitelli, but also many others. But the problem actually, the notion of non-reciprocal interactions is quite old, and in the neural nets literature and so forth, it is much discussed quite a long time ago, Hopfield and others. I'll skip this bit, I think. Yeah. Oh no, I won't skip this bit, I think. That. Yeah. Okay, now to start with. Hello. Supposing, and just to remind you of why detailed balance rules out non-reciprocality, even if you have a collection of particles, so let's imagine the following: you have some particles interacting with each other, and the particles are in a surrounding medium. In that case, if you just pick two of the particles in that system, there's no absolute rule that says that the forces they exert on each other have to be equal and opposite, because there is a medium around. Nonetheless, if those particles are interacting in contact with a thermal bath at equilibrium, the fact of detailed balance, which requires this condition on any string of transition probabilities amongst set of states, ends up leading via detailed balance to the existence of an effective energy function governing the dynamics. And once you have an energy function, it means essentially that everything moves downhill, down gradients with an energy. Okay, so even if you have particles which pairwise don't absolutely have to cancel forces on each other, in effect at thermal equilibrium, they and by extension, therefore, if you write down a dynamics of such a system consisting of particles governed by this force, by a force coming from potential, you will end up getting the force on, say, particle I due to particle J is minus that on particle J due to particle I. If you break detailed balance, you relax this condition, then in general you can imagine writing down dynamics that can have non-reciprocality in two ways. If you write down a dynamics with, let us say, simplicity, no inertia, strictly in a force balance form, then what you have is the forces involving the velocities and the forces coming from static interactions all balance out. In general, these forces will not be symmetric in this, and it will not be reciprocal in this sense. You can also consider another kind of non-reciprocality coming from antisymmetry of the what would have been damping coefficients if they were symmetric. But in general, the message of this opening part is just to point out that A, non-reciprocality is generic in systems out of equilibrium and is strictly ruled out in systems at equilibrium. You can imagine different kinds of non-reciprocality. You can imagine a system with multiple species of particles, and let's say the force exerted by particle of type A on particle of type B is different from that in the other directions. You could also imagine a system in which all the particles are the same kind, but there is some, externally prescribed direction. Let's say you've got particles on a lattice, the objects on a lattice, and it could be the particle sitting here and the particle sitting here have interactions that are not symmetric with respect to an identity defined purely by where they're sitting, right? So, species, distinguished locations, or some internal state. A long time ago, seriously long time ago, Jayjit Das, Madan Rao, and I studied non-reciprocal interactions in the context of a classical isotropic magnet. And recently, Nisarg Bhatt, a joint student with Subrata Mukherjee and me, and the three of us have been studying that model once again, in part out of the urge to explore its non-reciprocality in more detail. So the model is as follows, that you've got a lattice with sites labeled by n. At each site, you have a classical three-component vector spin. In this description, we've taken them to be strictly fixed length, but you can imagine a soft spin version of the same problem. Okay. Now, if this problem had been a thermal had been a Hamiltonian dam, we're not talking about a damped system right now. I'm going to write down microscopic dynamics, and any damping, diffusion, etc., will emerge by portraying that dynamics. Okay. So if the system had strictly Hamiltonian dynamics governed by the standard Heisenberg interaction, then you would have that the rate of change of spin n is that spin cross a local field coming from the neighboring spins. That local field would be the derivative of this energy function with respect to spin. And the whole, you could either write it that way, or you could just say that you have a Hamiltonian of this form, and the evolution of the spin is from the classical Poisson bracket of spin with the Hamiltonian. So this dynamics conserves the total magnetization and the total energy. The reason for the conservation of the total magnetization is the fact that rotation commutes with the Hamiltonian. The reason for the conservation of total energy is that there is a time-independent Hamiltonian. Okay. So we got, it's sort of in a moment of idle curiosity, a long time ago, these people, that is Jayajit Das, Madan Rao, and I, got curious about what would happen to this model if you change the rules of the game in such a way as to preserve isotropy in spin space, but make the interactions non-mutual. Remember that if you had so before I enter the enormous global part of the story, remember that if I had an antiferromagnet, then the dynamics is slightly more interesting in the sense that the total magnetization is still conserved because of isotropy in spin space. The total energy is still conserved. But if you had a system of this sort in an ordered phase, which I admit you don't have in one dimension, it's a separate matter. If you had an ordered phase of this system with antiferromagnetic interactions, then the transverse fluctuations of the staggered magnetization is also slow variable, right? So I therefore choose to define two objects. I'll say the coarse-grained direct magnetization I'll call M. The coarse-grained staggered magnetization, each at n, is something that alternates between +1 and -1 of the two sublattices. I'll call this N. So yes. But I guess people can interrupt during the talk. What are the rules of the game? As far as I'm concerned, it's fine. Yeah. Okay. So I guess this is just for notational purposes. This is the staggered magnetization. This is the regular magnetization. Okay. And you know that in that isotropic antiferromagnet, you have a dynamics in which the total magnetization is conserved. The staggered magnetization evolves in a field. The staggered magnetization and the direct magnetization beat against each other, and you get spin waves and so forth. And you know that if you take this system and coarse-grain it, then in addition to the terms inherited directly by coarse-graining the Hamiltonian part of the dynamics, you find relaxation and noise. The relaxation of the direct magnetization is diffusive. The relaxation of the staggered magnetization has a non-zero relaxation rate for the amplitude, but you know, of course, that the transverse fluctuations nonetheless relax in this manner. Right? And as a result, you get the dynamics that is well known in these systems. So now, what we did, as I said, is to consider a model in which so that's background. Consider a model in which spin n, which basically if you have a spin here, it has a different interaction with spin on its right from what it has with spin on its left. So now, because each of these guys knows right from left and interacts in a different way, this guy's interaction with this guy will be different from this guy's interaction with this guy. That guy is my right neighbor. I am that guy's left neighbor. So I'll get a dynamics which will look like this. The dOdt of Sn will be Sn cross Sn plus 1 with the coefficient J plus, and Sn cross Sn minus 1 with the coefficient J minus. So this is not an alternating exchange coupling associated with bonds, it's associated to which way you're looking. Leaving aside the question of why on earth we studied this model back then, note the following properties. Okay, the dynamics is still obeys spin rotation symmetry, but because there is no Hamiltonian to which you can say about which you can say that there is a spin rotation symmetry on the Hamiltonian, the question of commuting with the Hamiltonian and conserving total spin doesn't rise. Because there's no Hamiltonian, there isn't an energy either. Okay. Now, how might such a system arise physically? I would argue that supposing you have, let us say, a one-dimensional lattice with a non-centrosymmetric unit set. Okay, so there's some local structure which knows the difference between this way and that way. And you take a system like that and you homogeneously pump it with energy. So you hold it out of equilibrium in some unspecified way. So then the generic dynamics of such a system ought to have a term of this form arising. So maybe you have some, say, system and you pump energy through it by placing two faces of it in contact with different thermal arcs. Okay. So then this dynamics will emerge. So this dynamics is not reciprocal with respect to a fixed spatial direction, left versus right. And this model turns out to have no obvious stationary states. If you just study it, if you imagine setting it up in a uniformly aligned state, there is a ferromagnetic state, antiferromagnet spiral. None of it doesn't seem to like to stay in any state. It just evolves in a space-temporally chaotic manner. So we decided that we try to understand a little bit more about this model by looking at the extreme non-reciprocal limit, where J plus is minus J minus. And I've just set those to 1. So the dynamics you have is dsn over dt is Sn cross Sn plus 1 minus Sn minus 1. So in this limit, some surprising simplicity emerges. Advanced slide. Yeah. So to see what that simplicity is, let me define two kinds of variables. Let me define a direct. I've taken a slightly coarse-grained view. Let me define m with subscript n to be s2n plus s2n plus 1 and divided over 2, divided by 2, and n with subscript n be s2n minus s2n plus 1 divided by 2. So this is the direct and this is the standard manipulation. And let me define this weird object E sub n, which is s2n plus 1 dot s2n plus 2 minus s2n. Now, it's not an energy, but it is a scalar quantity. And a little bit of work taking this system with periodic boundary functions will convince you that the sum over all sites of En and the sum over all sites of n sub n are conserved. Now, I'm not saying this is based on some computation of anything with anything. I'm just saying I've written down a somewhat pulled out of the hat dynamics, and it happens to conserve these two quantities. And you can check very easily that the direct manipulation is not conserved. So you can then ask, okay, you've got this system, you studied it numerically and discovered it was chaotic. You discovered also that if you set it up in some simple uniform states, it's very, very unstable. Now you've discovered that there are two conserved quantities. And both these conserved quantities, they're not only conserved globally, you can also actually look at the evolution equation for each, which I'll do in a moment, and show that really what happens is that dynamics is local. That is, if they change locally, it's by augmenting neighboring regions. So is there a coarse-grained theory of this system with a kind of fluctuating hydrodynamics emerging from this? So this is the problem we decided to look at. Now, what you can do is the following. First, supposing I just take this microscopic dynamics and ask what m and n do. If I rewrite the s's in terms of m and n, and then naively postscript, that is where I have, and Where I have this term, I just replace it by m cross the difference when m is the neighbors. So if I do this sort of naive continuum limit, taking the existing terms in the microscopic dynamics and gradient expanding them and writing them in the continuum, what I get is that m dot is m cross del x n minus n cross del x n. N dot is del x of n cross n, and E dot is del x of this complicated point. Okay, so what does that tell us? That tells us that, first of all, it tells you, it confirms what I claimed to you microscopically, that N and E obey conservation laws, right? Because the rate of change of N is the divergence of a current, the rate of change of E is the divergence of a current. We are working in one dimension, so this object is, with respect to space, it's just a single component object. Its vector components are in the spin space, right? So you can then ask, this is the sort of bare dynamics by naively co-spinning the microscopic dynamics. What does the system actually do? Let's understand a little bit more about this system by looking at two aspects. One is trying to understand the way in which chaos spreads in this model. So we go back to the microscopic model. We take two copies of the system. One of them is perturbed at site 0 at time 0 in a particular way. And you compare the time evolution of the reference configuration and the configuration perturbed at one site. This is completely shamelessly borrowed from a study done by the ICTS group a few years ago. And what you do is you look at the degree to which these two configurations decorrelate from each other. So at time t equals 0, this thing is almost 1. And then as time, so 1 minus it is small, and with the passage of time, these two guys decorrelate completely from each other, and this decorrelator approaches 1. So what you ask is, how does this happen in this system? So here is a space-time plot of the decorrelator. Red is where it's essentially 1, dark blue is where it's essentially 0. And what you see is you perturb at a single site, and the region of decorrelation spreads linearly in time with a well-defined speed. So basically, you perturb here, and chaos or decorrelation spreads like this, and everything in here is sort of gone chaotic. Okay. So apparently, this system, even though the microscopic dynamics is deterministic, settles down into some kind of statistical steady state. Given the conservation laws that we discovered, presumably that statistical steady state is labeled by these 2 points: the total magnetization, total staggered magnetization, and the total pseudo energy, if you want to call it that. Given that this happens, can we, given this happens, and given that I told you there are these 2 conserved quantities, will it turn out that these guys actually obey some kind of nice, smooth, diffusive dynamics? You can argue as follows. You know that the direct magnetization is not conserved. So this microscopic chaos should lead to some kind of relaxation. So phenomenologically, you can argue that, an effective cosine theory of the system should have a finite relaxation time of the direct magnetization and some kind of noise, a non-conserving noise. So the effective dynamics of M should have this form. If that's the case, now you go back to the dynamical equations for N, which is d over dx of N cross M, and you say, look, this M is a fast variable. I'm going to replace it by its value expressed in terms of the slow variables, which are M and its principal E. And what will that look like? Well, I'll take this M equation. I've phenomenologically introduced this guy. So on timescales long compared to tau, although I don't know the value of tau, M is approximately M cross del x n. So I take N cross M, replace M by N cross del x n here. The N over dt is del x of N cross del x n. which apart from a projector to retain the fixed length of n is simply a diffusion with a calculable coefficient. So if you solve for the path n in terms of slow n, insert into the n equation, you get an emergent diffusion behavior for n. You can do exactly the same kind of thing for the pseudo energy as well. I won't labor the details of that. And so does this happen in the real system? Yeah. So here are, in the steady state, the staggered magnetization correlation function as a function of space at different times, 32, 48, 64 to 160, some units, and the pseudo energy correlator again in the same as a function of space at different times. And what you can see is the data is not brilliant, but the data collapse with the diffusive rescaling. If you plot square root of t times c but versus x over root t, it indeed collapses quite nicely. And if you look at the correlator at a single point at time t, it decays reasonably convincingly with the t to minus half. And the same for the pseudo energy. And so now I've planned my time so badly that I have zero time to talk about the next topic. So maybe I'll just state what we did, which is we showed that in a different kind of non-reciprocality, if you have xy spins on the lattice, and if the non-reciprocal interaction is between a spin with an orientation pi at site I and pj at site j, if the interaction is sensitive to which way this guy is pointing with respect to the separation vector between these two guys, it turns out that these spins, even sitting on a fixed lattice, end up advecting themselves. And the effective partial differential equation for the dynamics of planar xy spins with non-reciprocality with respect to whether you're pointing towards or away from something makes this orientation vector behave like a velocity in that it advects homogeneously in its own self. So you get effective Toner 2 style talking dynamics in a lattice of spins. Okay, I won't say more about this. There are interesting developments on this. I'll skip to the end. How to see. Start the slideshow. Yeah. Okay. So I told you one story and a teaser of another story. I showed you that if you classical O3 magnets with a strictly antisymmetric exchange, actually, the case I studied in detail, display a kind of thermalization. You get a statistical steady state, you get decorrelation spreading ballistically. So we don't know it's thermalization in some strict sense. We don't know whether this emergent pseudo energy generates the dynamics in any sense. We have no idea of any of that. We only know that the coarse-grained dynamics consists of smooth, diffusive behavior for the two conserved quantities that I mentioned. We don't know how to obtain this from a quantum model. We don't really understand the relation of this problem to other problems which to me smell similar, like non-Hermitian or PT-symmetric systems and so forth. The XY stuff I didn't tell you about at all. I'll be happy to talk about it later. Thank you.
Questions?
Hi, Sriram. I have a question regarding your the course grading that you did. And if I understood that you considered the non-conserved quantity, the magnetization as a fast variable, then you added the dissipation and the noise there.
Right.
But typically, isn't it that it would usually add the dissipation and noise in the conserved equation, because that's what also gives you the correlation?
Yeah, right. I didn't describe that calculation in enough detail. What you can do is you can introduce chronologically such terms in both the equations and do a bit of diagrammatics to get self-consistent expressions for the diffusivities, and you'll get a limited set of relations constraining the two diffusivities and the relaxation time and the noise strengths. You won't be able to predict the noise strengths because presumably their value is actually set by the zero energy, which is one of the initial conditions. And let's say for simplicity, you work with static magnetization equals zero, so there's no other parameter. There's essentially one parameter, namely the total conserved zero energy, and then length scales set by lattice spacing and so on. So, in fact, really what one should do is you should define a post-graining scale and prepare all modes whose wavelength is shorter than that scale to be passed, and write the effective dynamics of the slow variables in terms of passed. We don't exactly do that formal post-graining. We do a self-consistent dynamics, which introduces kinetic coefficients in both the equations.
And one quick
Hi. So I was wondering, since you have two conserved quantities in your dynamics, so if there was one conserved quantity, I could have imagined that on that sheet the dynamics is completely uniform or something. But what is the effect of the second? Does it constrain in any way, or does it?
I mean, in a weird way, it's not that different from what happens to the Hamilton dynamics of the ferromagnet, where there's a total magnetization and a total energy that's conserved.
But suppose if I take a fixed pseudo energy and fixed the other quantity, the magnetization,
Standard
magnetization, then I presume that you will get everything like decorrelation and all that.
Right.
Suppose I just fix the fixed pseudo energy.
Yeah.
And I don't fix the.
But how can you not fix it? Because the dynamics conserves it. So you would have to actually introduce a source either at the ends or something. The microscopic dynamics conserves this. So all you can. The point is, you can of course study. There's one way you could do it, which is you could study the behavior with a variety of initial conditions without keeping track of whether. Yeah, and at some level, that's what we do. For the most part, we've been looking at uniform. We've been choosing initial conditions from uniform distribution. But actually, we haven't honed in on one value of pseudo energy and one value of time magnetization. Probably statistically, we have been in effect working with at least the standard magnetization equal to zero total. Most likely, that's what we've been doing. We haven't been super careful about checking what happens if you study an ensemble of initial conditions not respecting one of the conservation laws. So I don't know, it'll smooth things out, smear things out.
I mean, in that case, I would have expected a certain kind of oscillation. It goes maybe up to maximum decorrelation and then it comes back, because one of the quantities is conserved and it is inbuilt in the dynamic.
Okay, I'm not sure. I have to think about that. Thank you. Interesting question.
Okay, I think there are other questions, but they're out of time. So thanks, Sriram, for the. So the next talk is by Klaus Troy, and we'll talk about post-screening suspension capacity from us.
Yes, yes.
Hello.
Yeah, I will just use it like this. Yeah. Can you make it bigger or not? It should stay like this.
Okay, let me start, and let me start by thanking the organizers, in particular the local organizers, who were incredibly helpful to me for organizing this conference and for inviting me to this very intense event. I'm very happy to be here, and I will talk to you a bit about a special system, an experimental system also, and you will see some experiments. And this special system are hot Brownian swimmers. And I show you a bit how they look like. And now you can't see the person anymore who experimentally analyzes them. This is from Stichhoff in his group in Leipzig. And so they can look like this, for instance. It's a half-coated polystyrene colloidal particle. And if you heat it with a laser, it will be asymmetrically heated, and the surrounding will have an asymmetric temperature profile. And it will propel, as you see in this movie, where they first have Brownian diffusion, and then they switch on the laser, and then it gets very fast. Still a kind of Brownian diffusion, but with a much larger diffusion coefficient. But in reality, it's really going in the direction indicated here by the axis, by the symmetry axis, and then the orientation is also diffusing, and so it is in the end using again, but much faster than without the light. So that is a hot Brownian swimmer, and I want to talk about, go through a couple of aspects of how we give coarse-grained descriptions of such a single thing and also many of them. And that's essentially that the theoretical work was done by three very good postdocs, I would say, but the one in the middle, Gian Maria Palasco, actually was a PhD student in my group, but behaving like a postdoc. And the other two were real postdocs. Viktor Olubac is in Prague, and Sarah Luz is now in Cambridge in my Kate's group. And they did most of the theoretical work together with some PhD students that you'll find in the citation. So the motivation for us is to somehow do what we know how to do for passive particles. If we have passive particles, atoms, or colloids, we can coarse grain a system of many particles to a coarser scale and still describe it in a very nice and efficient way. And it's clear that if this individual particle, the atom, is becoming a swimmer or is in another way out of equilibrium, this gets much more difficult and many things can go wrong. And we want to understand this process. And I have a nice quote from Eric Smith here about coarse graining, how important it is for our understanding as physicists. And yeah, that is basically what we want to follow here. And so a particular emphasis will be during the talk on effective temperatures and what we can do or can't do with them. So here is the theoretical description of such a particle. You see the hot particle, and you see a red temperature field surrounding this particle, and also the viscosity of the fluid in which the particle is swimming, small colloidal particle, is not constant anymore. So there is no simple notion of viscosity for this particle that is just a constant number, but there's a function similarly for the temperature. So the viscosity problem is more of a mechanical engineering problem. I will not discuss this, but the temperature problem or statistical mechanics problem, this I will discuss. And to make the link with thermodynamics, what goes wrong here is what is written there below, is that we lose the Searle's law of thermodynamics. Different degrees of freedom do no longer equilibrate with each other. And that will become important for the description. If we want to force grain, we have lost one of our fundamental laws of thermodynamics. Nevertheless, we can describe the Brownian motion of such a hot particle in the very same way as we describe the motion of an isothermal particle, except that we have some efficient coefficients. So there is an effective friction here, and there is an effective viscosity here, and there is an effective temperature down here. And the HBM always refers to hot Brownian motion, which which is the name for such Brownian motion of a hot particle. If you have all this, we also have an Einstein relation that links the temperature and the friction to the diffusion coefficient of such a particle. And yeah, then the question is, can we, what does this temperature mean? And it is a temperature in the sense of the second law of thermodynamics, not in the sense of the zeroth law, because this we have broken it, but in the sense of the second law of thermodynamics. And we can calculate it. To calculate it explicitly, we have to go to a more fine-grained description with a fluctuating solvent dynamics, so fluctuating hydrodynamics of solvent, and then we can try to calculate such a number here. And you see the leading term is the ambient temperature. Then there is a correction telling you that somehow the effective temperature for describing the Brownian motion must be somewhere in the middle between the hottest and the coldest temperature. And if you go to higher orders, you get more corrections. But those are pretty small for typical applications, because you are not heating your solvent by hundreds of Kelvin, but typically only by a few in most of the applications. And you also see that in leading order, this is like a universal number. And in higher orders, you get in kinetic information about the solvent and the solvent viscosity, and then it gets more difficult. Yeah.
Are you going to tell us what you mean by in the sense of the second law of thermodynamics? Are you going to actually?
Yeah, I will say more about that, because quite often people tell you different things, and I come more to that. So here, in particular, it means that you try to understand that you can mimic the dynamics of the hot particle by an equilibrium system that is not producing entropy. Like here, of course, the law of entropy production, because you heat the particle all the time, and the heat flows out from the particle to establish this temperature field. So there's a lot of housekeeping heat involved, and the fluctuations are also not those of equilibrium. But you can map it to an equilibrium problem, which is not producing entropy. And in that sense, you can say, okay, it looks like a normal Brownian particle with a higher temperature, and that's the higher temperature. And so you see there is a link to entropy, and that's how it links.
Just a small follow-up, which is that presumably this is true provided you don't resolve the dynamics of the orientation of the particle, because you've treated it as a
so here it is a homogeneous particle. We like in this case, you see it's a homogeneous. I'm coming through the swimmer in a moment. So far it is just homogeneous, but I can make it a swimmer, and then of course it gets more complex. So on this level of just a single hot Brownian particle, people have tested this prediction, like here in Frank Sillo's group in Leipzig. They have set up a very nice method, twin box, they call it, where they can test this stuff without parameters, and they get a very nice comparison with the prediction of that. Especially it's enough to look at the first order. You can want to go further and say, well, okay, I mean, if this is just like an equilibrium system at a higher temperature, maybe we can write a Maxwell-Boltzmann distribution with a velocity degrees of freedom, and here, like how the particle is distributed in a potential energy landscape. And then you see that you have to distinguish already two temperatures. So the temperature of the degrees of freedom that are velocity degrees of freedom are different ones from the ones that are station degrees. So that's why we lost the zeroth law of thermodynamics. They are not all the same anymore. They have different temperatures. And it gets even worse if you go to frequency-dependent things. Like this was a very slow Markovian dynamics description of the phenomenon. But if you go to high-frequency behavior, you will get something more complex, which is then a temperature spectrum, so to speak. So the description gets more involved, and it's a bit like in hydrodynamics. If you start with a sphere, you have a very simple friction law. If you pull the sphere fluid, if you have a cylinder or a more complicated object, you get more friction coefficients to describe it, and it gets all more complicated. And this kind of complications now infiltrate the description of temperature in the sense of the second law. So you get all the complications that you know from hydrodynamic kinetic phenomena. You also get them infecting the description in terms of temperature. So that limits somehow this project of describing everything with effective temperatures, because it gets just very nasty, and then you would not touch it anymore as a physicist at some point. You would say, let's leave it to the engineer. It's too complicated for us. So that's the basic idea of just hot Brownian particles. Now, if we break the symmetry of such a particle, as I've shown you in the beginning, we get a this I wanted to show you. This is how, for instance, if you want to calculate this quantity, it gets more complex, or more not complex, but more difficult, more work, more laborious. So if we now break the symmetry, automatically this hot particle, which was just a hot Brownian particle in the beginning, now becomes a hot Brownian swimmer. Now it is, because of the broken symmetry, it is swimming in a certain direction, as you saw already in the video. And of course, it's still fluctuating in orientation, and therefore the orientation is more fixed, but it's a swimmer. And then you describe it by the so-called active Brownian particle model, ADP. And so you see that the velocity of the particle is along its axis due to the swimming with a particle swim velocity, and there is some thermal noise, and also the orientation of the particle is diffusing. And of course, as I've said, there are these coefficients here which are effective coefficients now related to these different effective temperatures. They are different for translation and rotation, by the way, because these are different degrees of freedom. And but you get a very simple, in the Markov limit, a very simple description of this active particle, of this swimmer, and people can, in the lab here, they can look at the particle, record its orientation, and then decide when they want to switch on or off the heating, make it a swimmer or just a passive particle, and in this way they can decide where the particle should go, but they are not pushing it with forces, they are nudging it by just giving it fuel in the right moment when it looks in the right direction, so they can steer the particle without forces. That's what we exploit a lot in the experiments, like a Maxwell-Demon type manipulation technique for the experiments that we exploit a lot in these studies. Where we can look again, we had a zoo of effective temperatures and so on. And we also get something that Shriram mentioned a lot in his talk. If you have one particle and a heat source, or if you have two such particles, and they come together, they are the interactions are non-reciprocal to each other. Because it depends on how you're oriented, whether you're attracted to this guy and the other guy is not attracted to you because it looks away from you, something like that. So you immediately see that there should be non-reciprocal interactions in general. And this has then, of course, important consequences, as Shriram was already saying. So one thing where I want to go very quickly over is just that you can stack different types of non-equilibrium, as I've just done. So I've just already, by writing down these equations, I said, actually here we have these effective hot Brownian parameters, like hot Brownian temperatures. And the same is true if you want to go further to descriptions of stochastic thermodynamics of such swimmers, for instance. And we are very motivated by this paper here to analyze that. And you look at how much is it going forwards and backwards, this particle? Well, it's swimming, so it's mostly going forward, but sometimes the fluctuation brings it backwards and so on. So you can study the balance of these fluctuations, and you can check stochastic thermodynamic predictions like fluctuation theorems or fluctuation relations. or thermodynamic uncertainty relations, and these kind of things we have played. And so in a sense, with these effective Pott-Brownian parameters, you can stack up equilibria, go to more complicated non-equilibrium, stack up non-equilibria, and go to more complicated non-equilibrium. So I want to, in the remainder, look at two examples that make this a bit more vivid, or and show you two important aspects. So typically, what you have, if you have one particle, you want to have many then to understand what's going on. And we are doing with Frank Friedhoff a lot in this direction. I just give you these two examples. The first simple thing is you want to take this one particle, put it in a potential. But now, since we can change the activity, as I told you, we can also, instead of potential landscape, also look at activity landscape. So we have two things that we can be looking here, and the first one is like the interaction with a potential. And so you can imagine that you have such an active swimmer in a potential and you rock the potential. Or you have a passive tracer in a bath of swimmers, and again you rock the potential. And the two things are very similar. They look very much the same. And so you can build an active heat bath with that, like with these swimmers, and then have an active heat engine operating this active heat bath. And the second thing is I want to mention is that an effect that is not captured by these effective temperatures, that is redshift. And we'll get into that. It's about the passive and an active regions or a landscape of activity. Typically, you will induce polarization due to motility gradients of these particles that are not due to forces or so, but they are just kind of due to sorting of particles, and they lead to an observable non-equilibrium effect, which is called redshifting, that you get transport in asymmetric landscapes, activity landscapes. I will show you these. So both of these effects play a role in active heat engines. The second one that I just mentioned at the end, this redshifting, is used in so-called steady-state engines. So if you put such a gear inside a thermal bath, it cannot move, as you know, because that would be a violation of the second law. But if the bath is a bacterial bath or a bath of active particles, it will move due to this redshifting. There is another class of heat engines which are not operating steady state, like the gear turning constantly, but where you do this pumping or piston motion, so cyclic heat engines, as we discussed them a lot in elementary thermodynamics. And so these ones are kind of completely described by and explained by dynamically effective temperatures, and those here, like by redshifting, is a different thing. And people have made strong claims about these systems somehow beating the second law, and I want to convince you, and that's why I mentioned this. I want to convince you that you're not violating the second law. Maybe you are just not smart enough to calculate your effective temperature, and that's why you think you violated it. Or you don't understand the redshifting button. So I explained it a bit for the cyclic active heat engine. So as I said, the zeroth law is violated. Different degrees of freedom have different temperatures, effective temperatures. But these effective temperatures are consistent with the second law, and you can require this to decide whether an effective temperature is a good effective temperature. It's a good concept. And for that, you need a suitable thermometer. Typically, the particle like the active degree of freedom itself is a good choice for the thermometer. Here, the mean square displacement of this particle in the potential gravity parameter. And then you can operate the system, you change the stiffness according to some protocol, a Stirling process here, and you change the temperature of the underlying water bath, the real solvent, so you can change that. And the effective temperature will then do some complicated stuff, depending whether you operate it statically or fast. And the whole energetics of the system will then be determined by this very complicated quantity that you in general do not know, but in this particularly simple example, we could calculate everything. So there are just equations of motion for the H and the sigma, and from this, in the end, we get the effective temperature also. And so then you can see that things are consistent with the second law if you use this temperature. You are not feeding the second law with active particle gas. The other thing is this ratcheting or the polarization of particles in motility gradients. So here is the very simple example again where I have a passive and an active region. So here, if the particle is here, it's a swimmer, as in the movie I showed in the beginning, where first it was just doing ground motion. Then if you switch on the light, it becomes a swimmer and it's active. And so this experiment here was done again in the Statphys group, and it was done with a single particle. And whenever it moved from left to right, they switched on the laser, like automatically, of course. And then they switched it off again, and they had it running for days. And then you get the distribution of particles, and you see, okay, in the passive region, you have a high density, the active region where they run quickly, they go out of it quickly, and you have a low density. And similarly, you get this ordering or sorting of particles. So you get a high orientation of particles in a certain direction at the boundary, and also at the, like here, this is the let's say we look at this central boundary here. So you see there is polarization at this boundary, and this is caused by the activity, by the non-equilibrium currents in the system. And it's surprising, so to say, to see a polarization density pattern emerging that you wouldn't have in equilibrium. And it's not due to forces orienting the particles, but to sorting the particles at this boundary. There's also a funny thing. I mean, if the particle is active here, it's very fast. It has a high kinetic pressure, but it's not exerting this pressure into the passive region. Normally, if it is just a hard sphere, say, because at the moment it comes into the passive region, it stops, of course. It's no longer a swimmer, so it can't really easily exert unless it has a long-range interaction. Can't all this exert this pressure to the other side. So I only speak of the kinetic pressure, cannot be exerted to the other.
8 minutes.
Yeah, exactly. So this is a bit like, you know, in quantum mechanics classes, when you first learn to deal with a particle in a box potential, and you solve this, and it's very much the same calculation you have to do here to get these densities and polarizations and everything in this problem. So it's a very nice exercise, really, very close to what we are used to from our lectures. And there's a bit of a trick that we have to play because it's actually a bit more complicated than the typical textbook problems. But with this trick, we map it to a similar, simpler system or a run and handle system for the experts, and then we can solve everything. And then we can see that the physics is the same basically, and therefore the solutions are almost exact. Yeah, you can get simple analytical expressions for the, for the skin depth here, and for the jumps and the density, and for the strength of the polarization. So this sorting of particles is what is behind this ratcheting when you have the turning gear. And in the example of the turning gear, you have, of course, the gear is a hard object, so it is like a potential landscape, and you are really either you can say you are turning the potential landscape, or if you fix the potential landscape, you will produce particle currents. And by sorting of different particles into different regions. And so here is a even simpler ratcheting effect where we only have, there's no potential here, and there's also no dynamic change of temperature or dynamic change of whatever. There is just a static region here with zero activity, so pure diffusion. And outside there is activity. So we switch on the light here and we switch off the light there, so to speak. And again, a simulation. This is a simulation, it's not an experiment. But it's again a simulation just for one particle. So whenever the particle comes from here to here, it's just going from swimming to just normal Brownian motion. And you see with the color code already how you sort the particles, that you get a lot of particles trapped in this corner here, and you have less particles here. And there are funny vortices coming up in the way the particles swim and the orientation. And that also explains why you can't build such a redshift in one dimension. You need 2 dimensions. This is a topological thing. So you need at least 2 dimensions to get such redshifting in static or stationary activity landscapes. And so the equations are the same as before. Yeah, this is just written slightly differently with x and y coordinates here, but it's the same equation, and there is this rotational diffusion. And here is now the speed of the particles is given by a function that depends on the spatial coordinates. That's the difference. Before it was a constant. Now it depends whether you're inside or outside. And yeah, you get this rectification, and you get you can study the efficiency and the current when you get the maximum current and when you get the best efficiency and so on. And yeah, I have to skip and go further, and I come to my last slide. Okay, and just if you want to coarse grain further to many body theories, you have to do, as of course as Shiran did in his talk, you have to say we want to go to coarse grain field theories in the end, because that's how in physics we address all many body problems, not only in quantum mechanics of course, but also in classical mechanics. We need field theories if we go to many body problems. And so here is an example of a 2 species problem, species A, species B. It's a conserved field, as you see with all these nablas here. But the trick is now we use now these non-reciprocal interaction that we have seen arises for these swimmers. Don't know now whether this is a model for swimmers, it's just a coarse grain theory. But the important thing is here that the interaction between the A and B fields, you see there is this delta, which is the parameter that breaks the reciprocity. And this has fascinating consequences. You get an interesting phase diagram. Many people are studying these now, these systems that have looked at these phase diagrams. You get interesting transitions to interesting new phases. So in particular, you get dynamical phases, so traveling waves, and you get hot bifurcations and exceptional critical point transitions if you go across these boundaries. Am I already using my discussion time? Oh, sorry. No, then I have to really stop there. And yeah, we have studied the entropy production there actually, but I'm stopping. I'm sorry, I didn't understand this. Okay, sorry. Thank you very much for your attention. Have a good day. Very short.
In the very first problem of a homogeneously heated Brownian particle, isn't it, given that it's in a fluid medium, isn't it possible that its dynamics acquires some kind of non-locality, that even there the currents set up in the ambient fluid spoil an effective equilibrium description?
Yeah, but if you take into account the flexion terms, like really, like in the hydrodynamic sense, that would spoil that, this sphere. But yeah, it's a very good approximation for a real nanoparticle. This is an excellent description. And even if you go to short times, you still neglect flexion. Like I said, the particle being here and the flow heating field being back, this kind of delay problem that would make it, of course, non-reciprocal in that sense, or break the symmetries. This we neglect, and we can't, so otherwise we can't calculate it, right? Yeah. With that fraction, it's non-linear hydrodynamics.
A very quick question.
So in the example of where you had the coexistence of passive and active systems,
Yes.
So in that example, it was for ABP system, right? If I understood. So ABP has a thermodynamic pressure, and if you look at the passive system, it also has an effective pressure. So is there a pressure equilibrium then that you can test that which have an effective temperature description?
Yeah, you can. If you have interactions, then the pressure is also exerted on the other side. I was just saying, and be careful, because if you just have passive particles that are passive here and active there, and if they are just hardcore particles, if the active particle is jumping into the passive region, it has lost its velocity, so it cannot carry over the kinetic momentum from one side to the other. So that's the subtlety there. And you have to be a bit careful about what you mean by pressure is exerted or is in equilibrium at that point. That's my point. I hope it's clear. Thank you very much. I'm sorry I ran over.
Thanks. Thanks. Okay, so the next talk is a 15-minute talk by Julian Tramser, and she will talk about emerging measure scale flows and chaotic advection in this aspect.
What was in the direction of whatever with that section?
Hello, my name is Jan. I got the CMS position at the laboratory, but the work that I'm presenting today is from my last postdoc that was with Ludovic Berthier, and the whole work is a collaboration with Yannick Peter, who's now postdoc at Leiden University, Rob Jack, who's from Cambridge, and Ludovic, who's in the same lab as I am. And the work is about emerging mesoscale flows and chaotic advection in dense active matter. And to be specific, because I will forget it later, it's all in 2 dimensions. And what I will do is I will introduce one more time what is active matter to also define some quantities I need later. So in this animation here, you can see 2 particles. The blue one is performing Brownian motion, and the orange one is an active particle. I will just compare the 2 kind of motions to highlight some differences. So you know that the equation of motion for Brownian particles in the absence of external forces has only one term, which is the noise term. And the noise is data correlated in time, and as a consequence, also the velocity autocorrelation is data correlated in time. And here I say it one more time very clearly that clearly know that for me the velocity is the r dot throughout the talk. Now, if we compute the mean square displacement, you know that it grows linearly in time, and we call this a diffusive scaling. And now if we look at the active particle, it behaves exactly identical to the passive particle at large times. It also diffuses in time, and the whole difference lies in the short time behavior, where the active particle moves ballistically up to a characteristic time scale, tau, that is the persistence time. And it's called persistence time because the particle persists to move in the same direction within this time scale, then only changes the direction. And there's an associated length scale to it, the correlation, the persistence length, lambda, which you can see here. So it's the average length the particle travels in the same direction before changing the direction of motion. And the mathematical model associated to this projector here is called active Brownian particles, which you have seen before already. So what we do is we assign a unit vector to each particle n that has an orientation theta, and then the particle simply moves in the direction of this unit vector with a constant speed v0. Now, the stochastic nature of this equation is hidden in the time evolution of the angle, which diffuses in time. And we have 1 over the persistence time in the diffusion constant, so that you see that as larger tau, the smaller is the diffusion constant. This means the slower the angle will change. That means the longer the particle will move in the same direction. Now, the velocity autocorrelation is in sharp contrast to the one of Brownian motion, because we have finite correlations at finite time. It decays exponentially with, again, this characteristic time scale. And you have already seen an example of an experimental system of active matter. But of course, these mathematical models are inspired by experimental systems like these walking grains that have vibrated, and due to the asymmetry in the feed that you see, they perform this persistent motion, where you can see here some particle trajectories. Now, in active matter, we are not only interested in the single particle behavior, but very much so in the collective phenomena that emerge when we put many of these particles together. And the phenomenon that I want to concentrate on is what you see in this movie, where you don't see that much because it's a little bit delayed, unfortunately, that I'm connected via internet. But anyway, so the state that you see is an suspension of bacteria. And they are rod-shaped, and they are in a state that's called active turbulence, mesoscale turbulence, or bacterial turbulence. And you can see some snapshot of the vorticity of this system here. And the name turbulence is really inspired by the resemblance of the motion, and not by the physics that is creating or even determining the motion. So people saw vortices and streams and got reminded of inertial turbulence. And these bacteria here, they are rod-shaped, and it has been argued that the alignment that is happening due to this anisotropic shape is necessary to create this turbulent-like flows. But they are very different active systems that perform a very similar dynamics, but have very different interactions. Like, for example, here, tissue of cells. And now seeing this turbulent-like motion reappearing again and again in different systems can make us wonder if active turbulence is in the end a generic phenomenon of active matter. And then also should appear in simple model systems. One can also turn it the other way around and say that if active turbulence if active turbulence is a standard, is a standard feature of active matter, it should really appear in the standard models, like active Brownian particles. And here I'm writing again the equation of motion. So this is the self-propulsion, and I'm stressing that self-propulsion is strictly independent between different particles. And we have the steric forces, which are now isotropic, so no anisotropic shape, and thermal noise. And the phase diagram of these particles, or the phase behavior in general, has been studied intensely. For example, here on the y-axis, you have the activity, and on the x-axis, the density. At high densities, you find a phase that is not a disordered liquid, but it has some degree of order, so in 2 dimensions. That's why it's not a crystal. Then at intermediate densities and high activities, you find a phase-separated state between a gas and a dense phase, which is a purely non-equilibrium phenomenon, because to see such a phase coexistence in equilibrium, you need attractive interactions, but here you have purely repulsive particles. And the rest of the phase diagram is a liquid, so what is white? Now, where in this phase diagram could we find correlated flows that resemble turbulence? The correlated flows or collective flows, they require at least that the r dot, so the velocity, has finite spatial correlations at macroscopic length scales. Now, looking one more time at the duration of motions, I said that the self-propulsions are strictly independent between particles, so correlations in the velocities cannot emerge from correlations in the self-propulsions, they don't exist. Then we also know from equilibrium that correlated velocities cannot appear from steric interactions alone. So as a conclusion, if these correlated flows exist, they have to come from an interplay of self-propulsion and crowding at high densities. So where we could find those flows is at in a highly persistent, dense, active fluid. Now, if you look one more time in the space diagram, then you see that it's actually quite tricky to be in a dense fluid and very active at the same time. So starting in a dense fluid, you increase the activity, and the main problem is that you always end up in this phase-separated region. You could try to avoid it by increasing density and like going around it, but then you end up in this ordered states, which are fairly arrested. So what we would like to do is we would like to take this liquid corner here and push it up to higher and higher activity. And this is indeed possible, even to push it to arbitrarily high activity if you tune activity in a different way. So in the space diagram, what you have actually on the y-axis is the amplitude of the self-propulsion, and there should be a third axis, which is the persistence time, and even a fourth axis, which is the temperature. So like this, authors here, they chose to fix the persistence time and increase the amplitude of the self-propulsion, but you can make easily a particle more persistent by fixing the self-propulsion and increasing the persistence. Now, the phase diagram that I'm showing you here is yet another slice through this high-dimensional phase diagram, where activity is tuned by increasing the persistence time, and at the same time, the self-propulsion actually decreases in a specific way, but the persistence increases overall. I can give you details for this later. And for the experts, this is actually a phase diagram of active organic particles. But like the takeaway message for this is that it takes a lot of fine-tuning, but you can reach there to have between the MIPS, like the phase separation here, and the arrested solid, a liquid corridor that goes up to arbitrary activities. And in this case here, the arrested solid is actually an amorphous solid because particles have different diameters. So the emergence of order is frustrated. So now we can explore this liquid corridor and go in the liquid to very large persistence. And what we find is indeed, like here, maybe you see it a little bit better, these correlated flows that emerge and have, again, like streams and vortices of various sizes. And here you have, again, a snapshot of the vorticity of the system. Now we can quantify this correlated flows and measure lots of quantities, but because time is short and I'm talking way too fast, I'm sorry. I could have shown them more things. Well, I will focus just on one aspect of these flows. So in inertial turbulence, like the turbulence that is actual turbulence, what happens is that you inject energy on the scale of the system, and then energy cascades down to small length scales where it can be finally dissipated. So you have like big vortices, and this big vortices split down into smaller vortices up to a length scale where it can be dissipated, energy can be dissipated. And that happens in a new universal way, such that the energy spectrum, what I'm showing you here, follows a power law. That means real inertial turbulence is scale-free. So you have only the dissipation scale and the system size, and otherwise there's nothing in between. And these active systems, they are certainly different already because energy is not injected on a large scale, but on the microscopic scale of the individual particles. So energy injection happens here at small scales. And then energy has to basically cascade, it's an inverse cascade, up to a typical length scale. So these flows that you see are not scale-free. They have a typical correlation length beyond which the system is uncorrelated. But we can tune this correlation length by tuning the parameters to the arbitrary size. And with this, I want to conclude my presentation. So what I have shown you is that active turbulence appears in minimal model systems that do not have any alignment interactions, which was always put in previous models to see this emerging flows. So we can consider active turbulence probably as a generic feature of active matters. Then the flows are generated by these inverse energy cascades and are not scale free, but we can scale them to arbitrary large sizes. And what we also did, we actually started the second model that I have more time showing you, but this has feature kind of alignment. It's a Brownian system with feature kind of alignment. And it has not only qualitatively, but quantitatively very comparable flows, so that we argue for a new class of turbulence where theory actually is. And with this, I want to thank you for your attention, and again, my collaborators for this work, and especially Ludwig Berthier, who employed me in this last postdoc and was here all the funding. Yes, thank you for your attention.
Yeah, about this difference which you mentioned near the end. If I remember correctly, in PP turbulence, you do have reverse cascade.
Yeah, you can have reverse cascade, and if I'm not mistaken, you have to rotate the system, and then you can get reverse cascades.
Not sure about that, but yeah. But there is a difference between 2D and 3D, forward versus reverse. In 2D, you have a reverse cascade, energy cascade.
In 2D?
Yeah, and your system of active matter is also 2D. So
yes, it's
there seems to be same, if I'm not wrong.
I think in general, in inertial turbulence, energy always flows to the small length scales because the energy is injected at the size of the system, except when you rotate your entire system, and then you can make energy really go from small to large scales. But for this, you have to rotate your system, if I'm not mistaken.
Any other questions? So I have just one question. I mean, so like experiments seem like in some experiments like with battery or something. There are experiments, right? Sort of.
Yeah, there are a lot of
but is this kind of this model that?
This model, well, it's an underdamped model, so it's like the overdamped. Sorry, it's the overdamped Lagrange equation. So it's like the most simple thing that you can imagine. I don't think that someone had really an experiment that is exactly like that, but there are actually experiments of spherical bacteria also. So like basically this, which okay, you don't see it, I'm sorry. Like on my laptop, just kidding. This looks very similar, and you see it's not as dense. But there is fluid, and there are hydrodynamic interactions. And while the bacteria, they are round, but they have a flagellum, so it's again a question how spherical are they really? But yeah.
Okay, so I think we're out of time. Thanks, Julian. The last talk of this session is by Manas Khan, and he'll talk about how active are active Brownian particles in confinement.
Hello. First of all, thanks to the organizer for giving me the opportunity to talk about our work here today. And this will be a very brief talk, so I have to pass through my slides. I apologize for that, but all the interesting details are in the details of the experiment and all I will say. So if you have any questions, we'll discuss the details, the final details later. Today I'll talk about how active are active Brownian particles in confinement. Let's first start with simpler questions. So what could be a good measure of activity? Will it be the velocity or the stated length scale or time scale for three cases? And when they're in confinement, either 2D or 3D, then the velocity gets affected by the confinement. So is the dimension of the motion or the dimension of the length scale of the confinement that matters, the time scale of the motion or the time scale of the confinement? So things becomes complicated, and it becomes even trickier when we have noise in the system. So there is a fundamental difference between those systems I just showed you and the system we work on. Our systems are microscopic and thus thermalized, so there is downward fluctuation in the system. So we have activity plus noise, and we are interested in this case. So we have been pursuing a similar problem, and then it became a prerequisite to know that how active are active downward particles in confinement. It has two parts. How to define activity in this case? That's a very important question. What controls it? So when we have been searching for the answer to the first question, we saw this one, this article. So here it was argued that if the steady state probability density has a peak at 0, then it will be more like a passive dynamics. And if the peak is added from 0, then it will be more like active dynamics. Slightly different system, but similar inferences that if the peak is at 0, then it's passive like, and if they are like confined in an annular region with a peak or not in the middle, that will be more or less active. These are the trajectories. But frankly speaking, when we read through the papers, we couldn't understand them completely. We couldn't understand the logic behind defining this passive and active depending on the probability distributions at steady state. Today, I have the opportunity to interact with some of the authors here, and then probably I will understand them better. So the first question got redefined for us, that is steady state positional distribution a reliable measure of activity or not? And the second question remains, what controls it? So here I will define the system, but I don't really need to because the previous talks did that for you. So this is normal Brownian motion, or call it Brownian motion, passive Brownian motion. And this is active downward motion as we see it under microscope in the lab. What are the fundamental difference in the dynamics? So here the step sizes are random following a normal distribution. Here, if it's dominated by activity, then they are constant because the speed is constant. Because the propulsion speed is constant, and the direction is associated with the direction of the particles, so that's particles orientation. And here the velocity of propulsion for a passive downward motion decays at a time scale called the Brownian time scale, and for an active Brownian motion, it's slower. Its decay time is called the persistence time, which is inverse of the orientational diffusion coefficient. So in case of free Brownian motion, the activity is measured by the vector number, which is the velocity, that this is the speed of propulsion, divided by root over dt times dr. dt is the translational diffusion coefficient, and dr is the orientational diffusion coefficient. So here I also define the confinement. This is the characteristic time scale of the active Brownian dynamics. Here the dynamics gets randomized at tau greater than, or the time scale greater than tau r, which is the persistence time. So up to tau r, there is persistence in motion. After that, it gets randomized. And here, this is the characteristic time scale would be tau k, where a Brownian particle, a passive Brownian particle, is the confinement. And their associated length scale. This is the persistence length. That is the associated length scale here. And this is the confinement length. So this is root over this length scale. So this is the confinement length here. So there are other studies, similar studies here. So this was probably the first one, where they studied active Brownian particles in two-dimensional trap, and they also showed similar steady-state probability distributions, but they did not define which one is more active or which one is more passive. And there have been other theoretical and simulation studies, mostly with correlated noise-driven active dynamics, which are active positional processes. But there is only one experimental reporting so far that's not with Brownian motion or Brownian system. This is inertial system. This is a toy robot. It's called Pixabag Nano. It's a very tiny thing. And this, they track the motion of it on a parabolic surface. This is a dish antenna that we install on a rooftop or TV reception. And by analyzing the dynamics, they showed that there are two types of dynamics. One is orbital, so it goes round and round at a particular radius. And then this is climbing dynamics, where they go radially outward, and they then analyze the theta component. So now I'll talk about our work. Before I do that, it's mandatory that this project is funded by ACRD, and I will talk about Sanatan's work today. He has done analytical calculations, simulations, and experiments all simultaneously. So this is the description of our system. This is the Franklin equation for x, y, and this is phi. This is a quasi-2D system. Phi is the orientation of the particle with respect to the x-axis. These are the random velocity component because of thermal fluctuation. These two terms comes from the confinement. So this is the time scale. This is the equilibrium time of the confinement. This is harmonic potential. These are the restoring forces. Velocity coming from the restoring forces, and these are the active propulsion. This is cos theta, the cos phi component because this angle is phi, and this is sin phi for y. And this is the orientational diffusion coefficient governing this equation, and the inverse is the persistence time. So from that, you can get the instantaneous position xt or yt. If I write the equation for yt, then I will get a sign here. And for one-dimensional mean square displacement, we just take the correlation and calculate this. For one-dimensional mean square displacement, we will have not so good-looking sine and cosine correlation terms. If we add them up, we can get rid of those terms, and this will be fairly good-looking and compact form. So this first part is coming from the HBPP, and the second part is coming from confined activity. When t is greater than tau k, the dynamics get confined, and this term will go to 0. At t greater than tau r, which is the persistence time, and then the dynamics will become symmetric. This term will go to 0. When t is greater than both these time scales, then it will reach a plateau, and the plateau will consist of these two terms. This comes from, again, the passive part, and this is from the active part. Here you can see the propulsion speed. So it suggests that the dynamics is mostly governed by the time scales, okay, more than anything else. In experiment, we use a half-coated particle, a silica particle. One side, one hemisphere is coated with platinum. So we generate activity by cell diffusion process. When we put H2O2 in the suspension, then H2O2 gets distributed into H2 and O2, and because of the concentration gradient, this will fill up a pulsar. So this is called cell diffusion process. And then because it is exposed to a laser field, we create the confinement using optical trap. So this part is more heated, so there will be temperature gradient, and there will be cell thermophoresis, and this will fill up a pulsar because of cell thermophoresis. The cell diffusion process is characterized by the concentration of the hydrogen peroxide, and if I increase the concentration of the hydrogen peroxide, the propulsion will be more. Similarly, the cell diffusion process is defined or characterized by the laser power. When it goes away from the center of the strap, then it decreases, the propulsion decreases, and also if I decrease the total laser power, then also the propulsion will decrease. Now is the trickiest part, when we use a harmonic potential by a focused laser beam to trap the particle or to create the confinement for a simple isotropic particle which doesn't have any coating. So it will feel a conservative force field because of the gradient force, and it will get trapped here just at the center. That's the stable point. But because this platinum coating, everything becomes asymmetric. So there is enhanced scattering and asymmetric scattering force, asymmetric gradient force, asymmetric thermophoretic force. And then the stable configuration of the particle in optical trap depends on the balance of these three asymmetric forces. That's very complicated and very tricky. That's why we haven't seen any other experimental paper probably so far. It's very difficult to keep them in the trap for a few seconds, but we had to record few minutes video to analyze them. So here, because of this setup, the activity and the strength of the harmonic well gets coupled, because if I want to increase the strength of the potential, I have to increase the laser power. That will increase thermophoresis, and the activity will also get increased. So we change the laser power and the H2O2 concentration to scan through the parameter space. So when we have high laser power in absence of H2O2, we have dominant harmonic confinement, self thermophoresis, and a pretty less asymmetric optical force or moderate asymmetric optical force. When we have lower laser power in regions of H2O2, the dominant thing is self diffusion process, harmonic confinement, and self thermophoresis are moderate, and asymmetric optical forces are less. So this is how they are realized. Here, this is 1.21 milliwatt of laser power, 2.5% H2O2. Here, this is the laser power. So using these two, we have increased the ratio of tau r by tau k. And then here, it kind of fill up the space. Here, this is the center. It stays away from the center. It will be more apparent when I show you the trajectories. These are the trajectories. These have been realized with this kind of configurations, laser power and H2O2 concentration. These are the steady state.
What kind of confinement you have?
Harmonic. So these are the steady state probability distribution. These look very similar, this part and this part look very similar to the steady state probability densities that I showed in the references at the beginning. Okay. So if I look at the velocity, then velocity doesn't play much role here. So it's the tau r by tau k ratio that increases monotonically from this to this. So here we have a dynamical transition depending on the ratio of tau r by tau k. So here at the mean square displacement, that fits quite well with our analytical calculations. And from the fitting, we get the parameter tau r, tau k, and v. And then we have analyzed the velocities. So this is the theta component, the azimuthal component, and this is the radial component. Here for tau r by tau k, very, very less, 0.09. Here it's large. Here we show that the velocity can be fitted with two Gaussians. They are away from the center. And this value, the position of the peaks, very much matches closely with the RMS value of the velocity. So these dashed lines represent the RMS value of the velocity. And here, in this case, when tau r by tau k is large, then it's a single peak which lies at the 0. So here, velocities are more. On average, here velocities are less. So the activity gets suppressed. It looks like the activity gets suppressed with increasing tau r by tau k. What is actually happening? Why the time scales are so important? So when tau r is very greater than tau k, then confinement happens faster, then the particle reorients. So particle doesn't reorient much. It goes at the periphery. It starts like it moves along a persistent direction, and then it moves a point. It reaches a point where the drag force gets balanced with the restoring force. Kr is equal to 6 pi eta av. Then it slowly diffuses at the periphery, and it's in the confined, this angular confinement. But here, when tau r is very, very less than tau k, then the active motion gets randomized faster. Before it experiences the confinement, it can reorient itself and then it can fill up the whole space. That's what our simulation shows. So this is a Brownian dynamic simulation. Here tau r is very, very greater than tau k, and here tau r is less than tau k. Every particle is associated with two arrows. The red arrow is the orientation of the particle. That's the direction of the propulsion, and the blue arrow is the direction of the instantaneous velocity, the resultant velocity. And then you can see that it will diffuse along this angular region where 6 pi eta is equal to kr. These circles are not physical confinement, those are imaginary lines. This denotes the radius where 6 pi eta is equal to kr. And here it can fill up the whole space. If I show you the trajectories, then it looks like this. Here in simulation, we can gradually increase the velocity at a particular tau r by tau k, where the ratio is 1/10. And this is the steady state probability. Velocities here, as I showed you for the experimental case. So here there are two peaks, and you see the RMS values are around 7. If you add them up, it will be close to this, the components. And here the RMS values are pretty less. You can see that it's almost 1 micron per second. Here it's almost 1.5 micron per second, whereas it's like around 7 here, though the velocity is same for both the cases. So when the trajectory is like this and the steady state probability distribution is this, we have more velocities here. Okay, and here it's more noise dominated when we have this kind of probability distribution here. Okay. Yes. So these are the displacements just spot on with our analytical calculations. So just before concluding, I will try to say that this dynamical transition is not only an active to passive transition, it also is a weak to strong ergodic transition. This is a very interesting story. I will tell you about this another time. Thank you for your time.
Any question?
So the velocity distribution that you measure, is it from the trajectory only, or
Yes,
from the trajectory?
Okay, so I think
One small question.
Yeah.
In the theoretical world, in the theoretical world, it's a parabolic potential, right?
yes,
And the maxima is at some finite radius. The maximum of the probability.
the next.
The ring.
Yeah, those are from simulation and experiments. In theory, we can get only the probability distribution at terminal cases, not the general case.
So should you experiment even a hard variant, right?
We don't have any hard barrier.
You don't.
So these circles that I showed you, those are the imaginary lines at which those two forces are balanced.
Okay, I think we can continue the discussions about break. So let's thank all the speakers.
Just a quick announcement. We have arranged for a meeting room in case some of you would like to discuss. So this is at the other end of, just opposite of this, or the opposite side of the corridor. Signs are given there. And another is some of you have found a declaration form in your registration kit. To collect those forms, there will be a box kept outside. So you can fill it in and you can drop it there. Yeah, and for those of you who haven't registered yet, please do registration. Thank you. Speakers of the next session, could you please upload your talk in case you are giving the talk from here?
Yeah, I agree.
Even though there is nothing inside the wall, that would always work and to treat that's personally, but 10.5 states in the middle. So if you have a effective function, you should also have it in the strongly particles and in other, you can mention other models like those. And they will all have it. So it's like the first thing is that you don't need anisotropic steric interaction or any kind of alignment. And the second stage is actually
different things. Is there any different things properties of tablets from this?
Yeah, so
like
if you look at the spectrum, this is for the it's like the acid K, then it's much slower than any other
So usually it's like it would be larger than one. And it is It says that you can and how do you achieve the time? You can understand that. And like what is the systems are very difficult to first we have to have systems that can there's no you find that we'll have a kind of force balance between this country and one region, where this whole thing is almost saturation. But then there is a small component from the sun functions. So you have like a small natural
This is the part when you have G equals to 0.25 from backward. Then this middle side is 50. So at time 51 to 45 travels like 8 units of distance. So that's surprisingly when you like speed to
then we find is that it really doesn't change the first
I mean, yeah, the function of see that also if you then 8 and it's only so but just here is given 6 times 0.6.
Yeah,
No, so if expectation the Asian thing won't collapse. Yeah, it will be it's faster, so faster. I think I recall we were discussing this one and they saying initially with something. No, actually so I thought why particularly faster. So I met
now
there was sometimes it's always so because of that you're talking about the last one. Yes, so and still like long times it's always yes, but short times it was ballistic. Yes. It's super. So short time it's always
get last transition of
We studied gas transition in Patti, and what we found is that we can measure the reactivation time, and it goes super exponentially fast as the density. And
so it's a really rapid transition.
and then we try to find the reactivation time goes. And one thing we find is the power of divergent form. We try theory, and it works well, but the exponential thing is something important for physical system. And I was wondering if, and so far we just have certain external information. I wonder if other system models may show clear gas transition. Yeah, that's why. Sure. You can go to the archive. Yeah, so
Now go.
I think the was there, but that's what I should
yeah, so please go over your find your space there. Okay, we found four vectors. And actually we had before I had a look like because we also had consider the repetition time and calculate the repetition time. Right. And so thinking that they have different so at this point, you have more than the repetition time diverting. First, they have another position.
expectation screens.
Right.
So that's why.
Yeah.
So, first orientation screen and then.
Right. Then the intermediate grasping where only orientation can be treated. Yeah. And then there is a second position. The position actually varies. Right, right. If you want, you can.
You don't have to read from this.
It's here, but if you want, I can show you. But what happens is that we have so bacteria are already very much fat, and the orientation doesn't change. Particularly near the domain border, some bacteria manage to move a little, and they can actually have a possible that they can how that system. And they also made up the dynamical sustainability. And you know, this quality shows that each is a class foundation. And we see that. But in addition to that, we also see for small functions, which is other than the and we argue that this is probably due to the collective motion. So what we see is that in the active treatment, bacteria do move in a collective manner. So they have a positive distribution. Yeah. Well, the implemented system is ready. And that set up how we culture the microorganisms. In that way, we can make bacteria proliferate and very compost make them proliferate and grow and die. The packing fraction is continuous.
So you have what I it's like this system.
So you yourself.
So you have more like this. So you also see like then slows down this point.
It's very. I think we have only 5 minutes. We got my time.
Yeah, for sure. Thanks to
তাহলে দরজা খোলা তো দরজা বন্ধ করা হবে আচ্ছা আপনার কাছে কি ইয়ে আছে ভোটার সই করা হয়ে আছে না না এছাড়া কিভাবে
You can upload your you can send a mail to Arnav Saha to his mail ID. জি, এই সেশনটা আমি শেয়ার করব। ওটা আমি কিছু দেয়নি। টাইম মিস করতে হবে। এইটা তো একটা আধ ঘন্টা বাকি সব 15 মিনিট। এরা 3 দিন লাইন টকের মাঝখানে যখন আপলোড করাটা কিন্তু কাউকে দেখতে হচ্ছে। আচ্ছা এরা কি এসেছে? এরা কেউ টক দেয়নি। আপলোড করে আপলোড করে দেবো। Because the life is okay.
No, that one is very No,
লাস্টের জন্য আসেনি মেল করলে কি হবে? হ্যাঁ মেল করলে হবে। পেনড্রাইভ আছে সাথে পেনড্রাইভ আছে।
Nutrition has given. Nutrition is online. Okay.
That's it. Please upload your phone. Actually, আসেনি শুধু সাথে দিয়েছে সুমিতা You can name them. So you have to join for our white side, yeah, and join for you can share. Thank you for
Very sharp. Yeah. I don't think that you added
That's what Oh, is it my? Right. Yeah. But has to be conservative.
it should be conservative, right? So the term,
Yeah.
I get in I'm not trying to see
Yeah, it's not a distance. It's supposed to be. Yeah, but then it's some fixed things.
Most of it's all the same water.
It's the same.
But I go to now acid.
Yeah, but it's even if it's still the same. Excuse me. Oh,
So start because and we don't find the in the subtract the now it is fluctuation in all the other Right now, we are doing this course training. Just pure phenomenology, but it really captures Then
obviously,
So welcome to the second session. In this session, there will be 5 talks, although the last speaker is still missing. The first talk will be an half an hour in duration, and the rest of the talks will be 15 minutes. So the first talk is by Statphys, and he is going to talk about condo interaction of quantum spin Hall H channels with charge particles. Statphys.
Hello, am I audible? Okay, seems. Hi, so good morning, everyone. As said, I'm Statphys. I'm from SNBO's National Center for Basic Sciences, and today I'm going to talk about condo interaction of quantum spin Hall H channels with charge particles. So I will apologize in the beginning if the talk appears off topic for many people. But I am a condensed matter physics with expertise in quantum transport phenomena in low-dimensional systems. So this is what I'm going to talk about. And for the past few years, my interest has been topological systems, more precisely two-dimensional topological insulators which host quantum spin Hall H channels. And I'm an experimental physicist, so I will talk about the experiments which we have done in two-dimensional topological insulators. And I joined SNBO's in about a year back. So that is why most of the work which I present will actually be something which I did during my postdoc in collaboration with my postdoc supervisor. So before I move further into the talk, as I said, I will acknowledge already the people involved, even though I am presenting the work, and we can see there's a whole lot of people who are involved in this because it's a big experimental group. And I did the work with Professor Lawrence Molenkamp with theoretical input from Evelina and Yuka. And there's a whole lot team of people involved, which has started from growing the material to fabricating the devices to doing the measurements and the theoretical calculations. So before I move into the main topic, I would like to give a small introduction to what a quantum spin Hall insulator is. So I find it easiest if we recall the quantum Hall effect. So if you take a simple picture of an atomic insulator, we have electrons moving around the nucleus, and that leads to some energy levels with an energy gap in between. So if you take the quantum Hall effect. The quantum Hall effect is actually fairly simple to this, if you want to visualize it. If you take a two-dimensional electron system in a magnetic field, then we all know that those electrons form cyclotron orbits. And those orbits in the bulk of the material will remain fixed there, localized there. However, orbits, so if we do the full Lagrange level calculation, full calculation of Schrödinger's equation, then we'll have a similar picture. We will have energy levels which are separated by the gap. However, a slightly different picture happens at the edge of the material. Within the bulk, even though these orbits are localized, at the edge, we see that an orbit, let's say if an electron starts from one point, it can hit the edge and then continue the orbit. In this way, this electron will actually be transported along the edge. So even though the electrons which are in the bulk, they remain localized, at the edge, the electrons actually move around. And turns out that the conductance or the conductivity due to this movement of electrons along the edge is actually quantized. It's quantized in units of E square over h. And the quantum Hall state is actually an example of a topological state. So if we take this picture, then a quantum Hall state is a state with a broken time reversal symmetry, because it's a state in which you have a two-dimensional electron system and you have an external magnetic field which breaks the time reversal symmetry. The question which I asked is what happens under time reversal? So under time reversal, the direction of motion as well as the spin of the electron will be reversed. So earlier, if we had an up spin electron which is moving in an anti-clockwise direction, then under time reversal, we have a down spin electron which is moving in the clockwise direction. It is as if the effective magnetic field is reversed. Now you take these two opposite quantum Hall states, two quantum Hall states for opposite magnetic field, and bring them together. So once you bring these two quantum Hall states for opposite magnetic field together, then you will have a state where the effective magnetic field is actually zero, and the motion of the electron, direction of motion of the electron is tied to its spin. So if we have a spin up electron, it will move in a clockwise direction, and a spin down electron will be moving in a counterclockwise direction. So this state at zero magnetic field, where we have counter propagating helical edge channels, which means electron of one spin type moving in one direction, electron of opposite spin type moving in completely opposite direction, is known as the quantum spin Hall state. And it occurs at zero magnetic field. And under time reversal symmetry, these states are actually protected against backscattering. We call that these states are topologically protected, similar to the quantum Hall state. Now, this was a cartoon picture of trying to construct a quantum spin Hall state. And the quantum spin Hall, the systems which host these quantum spin Hall states are known as two-dimensional topological insulator. Now, this was a cartoon picture of hosting a quantum spin Hall state. What we do actually, in order to realize this in a material system, we use a material system which is known as mercury telluride. And the way this mercury telluride actually forms this quantum spin Hall state is that, actually I missed a slide. Sorry, I will come back to this later. So once, as I said, this was a cartoon picture of making quantum spin Hall state. Then we come across, already there were predictions about what can be a physical system in which such a state can be realized. And the first paper which actually comes to mind when we talk about this effect these days is the Kane-Melle picture, which predicted the quantum spin Hall effect in graphene in 2005. They say that with the spin orbit interactions, there can be a bulk gap which opens into the graphene. Graphene normally, which is a zero gap material, you can have a gap in the graphene and counter propagating helical edge channels. However, if one does the calculations and tries to find out what kind of gap is open, then it turns out the band gap is actually only a few tens of microelectron volt, which means that even at very, very low temperatures, this is very difficult to resolve. However, way back in 1985, as I said, nowadays, when people talk about quantum spin Hall insulator, most of the time, the first paper which people say is the Kane-Melle paper. However, if actually one does a bit of more literature survey into the back, then it turns out way back in 1985, two Russian physicists named Volkov and Pankratov have already discussed such a phenomenon. So what they studied a system which is lead telluride with small amounts of tin in it. So if you see, this is the system lead-thin telluride, and they tried to study the band structure of such a system with varying concentration of this tin atom. So as you keep incorporating this, so if, let's suppose X is 0. When X is 0, it's pure lead telluride material. And then we have a certain ordering of the bands. Nomenclature for now is irrelevant. We have some ordering of the band, let's say L6 minus and L6 plus. But as you increase the concentration, then it turns out that above a certain concentration of tin, the ordering of these bands is actually reversed. If you see now, L6 plus is higher than L6 minus. And what they did was that they said, okay, we are going to study the interface of two materials which mutually inverted band structure. So let's take you have pure tin telluride with one particular band structure and lead tin telluride with an inverted band structure. And back then itself, they figured out that if we join these two materials, then to the lowest order, the band structure would be, if you join the minimum of this conduction band to the maximum of this valence band with a straight line, and similar vice versa for the other bands. So they already figured out that if you have an interface of two mutually inverted band structure material, then you will get these kind of topological states. And the title of the electron is actually two-dimensional massless electrons in an inverted contact. This exactly is what we now call as massless surface states or massless surface states of a 3D topological insulator or massless 2D edge channels for a 2D topological insulator. So way back in 1985, this was already done. So in graphene, it's difficult to observe. So what turned out later on, okay, there is a more feasible material system where the band gap can actually be slightly larger and people can actually observe this in experiments. And the material, this is the material system that we work with. So instead of using lead-tin telluride, which was shown by Volker with Pankratov, we use a slightly different system. It's mercury telluride with cadmium impurities added. So it was shown in 2006, which is soon after the Kane-Mellett paper, that you can have a topological phase transition as a function of thickness if you grow mercury telluride quantum wells and vary the thickness from about, let's say, 5 nanometers to tens of nanometers. Then at a particular thickness, you will have a quantum phase transition where you will transition from a trivial insulator to a topological insulator. And at the heart of all these predictions lies the inverted band structure of mercury telluride, similar to what we already showed, what I already talked about for lead-tin telluride. So for mercury telluride, this was also known way back in 1970s, that mercury telluride actually has a band structure. So mercury telluride is a zinc blended semiconductor, but its band structure is different from other conventional zinc blended semiconductor in the sense that if we zoom in at the band structure at the gamma point, then we see that the order of these gamma 6 and gamma bands are actually inverted. For a normal band structure, for a normal ordering of the bands, the gamma 6 would be actually higher than gamma 8. But for mercury telluride, we find that this is actually inverted band structure, and the inversion is about 300 milli-electron volts. So we took such a similar material, we made an interface of mercury telluride with mercury cadmium telluride by adding cadmium into it while growing. And if we grow such an interface of two mutually inverted band structure material, then you are expected to see this quantum spin Hall edge channels. So this was done in this experiment in 2007, and it was shown that if you actually take a quantum well which has the thickness in the right regime, where the band structure is inverted, then we will have conductance which is actually quantized to 2e square over h. 2e square over h because there are two edge channels which are flowing across the edges of the device. So each edge channel gives rise to one quantum of conductance, e square over h. So two edge channels means 2e square over h. Okay, now what I'm going to talk about is the basics of these fluctuations. So as I said already, that the conductance is quantized. So obviously you would be expecting that the conductance should be e square over h, but when it is actually measured in experiments, it is seen that it is no way close to quantization. You can say that conductance is order of magnitude is e square over h, but the conductance actually has fluctuations into it. And the rest of the talk will be devoted to trying to understand these fluctuations. So I hope that I've been able to give you an introduction of how to realize this, what a quantum spin Hall state is, and how you can realize this in physical material systems. And now we will try to focus on the origin of these fluctuations. So this effect, the quantum spin Hall effect, has been produced in this mercury telluride system many times. But what is common in all the realizations of quantum spin Hall effect, not just in mercury telluride, in other systems in which it is realized as well, such as tungsten telluride or graphene proximatized with high spin orbit material, is that the conductance is never quantized. It always shows these fluctuations around h over 2p square. Whereas if you actually see other examples of quantized conductance, such as the quantum Hall effect, here you can see here also we expect quantization, but the quantization here is almost perfect, in the sense that the quantum Hall quantization is known to be as so perfect that the quantum Hall resistance is used as a standard of resistance. And if we measure these quantum Hall plateau, let's say if you measure one quantized plateau as a function of density or magnetic field, experimentally people will call it as the most straight line ever measured. However, the same is not true for quantum spin Hall state, even though both the states are supposed to be topologically protected. But quantum spin Hall state will always have these kind of fluctuations. And our work is actually devoted a lot in trying to understand these fluctuations. So what we do actually, in order to, we take different device geometries and we try to measure the conductance as a function of gate voltage. What gate voltage does is that when we, so the quantum spin Hall material is separated from a metallic plate by using some dielectric. Once we apply a voltage onto this gate, it puts an electric field, and that actually tunes the chemical potentials through different bands. So it goes from valence band through the topological gap where you see this quantum spin Hall state, and finally into the conduction band. So what we see that even though in both the cases there are some slight deviation from the expected quantized value, but what is common is that the conductance shows these large fluctuations. So what we try to do, we try to investigate how this fluctuation changes when we change the temperature of the device. So what we do is that we start changing the temperature from about 20 millikelvin to about 2 Kelvin for both the devices. And we see that as the temperature increases, the fluctuations, the magnitude of these fluctuations goes down, which in itself is not surprising, because as you increase the temperature, you sort of thermally brought in a lot of things. So the magnitude of these fluctuations go down. But now if we take different sections of this gate conductance versus gate voltage curve and try to see what happens to each of these features individually, then we see that, okay, there is some pattern which is similar for a variety of devices which we investigate. So let's consider this. So first of all, we divide the conductance, we take one particular section on a small limited region of the gate voltage. And we say that the conductance curve has features which we identify as either peaks or valleys. A peak is where the conductance displays some sort of a maxima, and valley is something where it displays some sort of a minimum. So we identify certain peaks and valleys in this conductance, which are shown by these vertical lines. So these vertical lines are peaks. Then we see that every alternate peak actually is independent of temperature. So if you take a look at this particular peak, then it shows that there is a variation of conductance as a function of temperature. As we keep the system from 20 millikelvin to 2 Kelvin, the conductance actually increases over here. However, if we take the next peak itself, thus adjacent to this, then we see that, okay, the peak here is actually has a very weak temperature dependence. Even if I say that they don't depend on temperature at all, it has a very weak temperature dependence. Next, if we actually move to again a peak adjacent to this, then we see that it has a strong temperature dependence. Finally, the next peak again has a weak temperature dependence. So what I can conclude from this is that every alternate peak has a very weak temperature dependence. All the valleys, on the other hand, have a similar dependence on temperature. Now, once we actually, and this is similar for both the devices, this particular thing is very, very reminiscent of a Kondo effect in quantum dots, where we have alternate peaks showing weak temperature dependence. I will just repeat here what we observe, because this is the most important observation. So what we actually observe here, that if there is a peak with a strong temperature dependence, the next adjacent peak will have a very weak temperature dependence. We label the peak which has a strong temperature dependence as odd peak, and the peaks which have a weak temperature dependence as even peak. for reasons which will become obvious a bit later, because we want to compare it with the quantum effects in quantum dots, where the quantum dots will have either odd occupancy or it will have either even occupancy. Okay. So in order to establish this further, we actually we take these points and we plot the conductance, or rather delta G, where we normalize it with the high temperature value as a function of temperature. And we see that it actually does have a strong temperature dependence for both the devices. Of course, some of you can question that for this particular device, we see that your delta G kind of saturates below a certain temperature. This is basically, it's a slight experimental detail.
What is the reason for taking peaks, not the minimas?
Because all the minimas behave same. There is not much. So I will show the minimas also, the dependence of minimas at the temperature. So the reason it saturates is a slight tricky experimental detail. The refrigerator which was used to cool down this device has a slightly higher electron temperature. So in this,
it is the density dependence, or it is independent of the density?
which one?
This whole study, what is the density?
Okay, so we are actually in this region, which is in the bulk gap. So there are no bulk carriers over here. There are only one-dimensional edge channels. When we are in the band, the density is of the order of 10 to the power 11 per centimeter squared in the band. But we are focusing on this region where the density of bulk carriers is expected to be 0. Because we have conduction only across the edges of the device. Is it clear? Okay.
My strong belief that density will also affect something in this.
Sorry, say again.
My strong belief that density will also affect in this. And can take for different densities.
Okay, we'll discuss about it. Certainly. Yes. So, okay, so we see that for both the devices, the conductance actually is dependent on temperature. So this was only for the odd peaks. And if I take the even peaks, we see that the conductance here essentially has a very deep dependence on temperature. As someone asked, what about the valleys? We see that all the valleys are at similar temperature dependence. So nothing really, this also has a physical reason as to why it happens, but actually it is nothing extraordinary as different behavior of odd and even peaks. So to summarize, odd peaks show a strong temperature dependence, even peaks show a very weak temperature dependence, all valleys show a strong temperature dependence, and this actually is reminiscent of a Kondo-correlated quantum dot. So now I'll try to explain that these fluctuations happen because our quantum spin Hall edge channels is actually interacting with a nearby quantum dot, which forms naturally in narrow gap semiconductors. So what happens in this system is that normally if we have a system which is, let's consider this as a cartoon band structure of any material system. So we have this conduction band, we have this valence band. Now, when we draw this, we actually draw this as very smooth curves. But in reality, these are not smooth. There are always these potential fluctuations in this band. And these potential fluctuations sometimes are stronger. And these potential fluctuations happens because of growth defects. Let's say if you are growing mercury telluride. So you grow mercury telluride even though a very high quality or any material, if you exfoliate graphene for any narrow gap semiconductor, by narrow gap semiconductor, I mean the band gap is small of the order of, yeah, sure, I'll finish in five for questions. So in narrow gap semiconductors, what I was saying, I got disturbed. Yes, so I was talking about graphene. Also for any narrow gap semiconductors, and by narrow gap, I mean semiconductors which has a small band gap, few tens of milli-electron volts. So if you are growing a material, the material will not be perfectly grown. Some positions there might be an atom which is missing. So across layers of material, you will have growth defects and vacancies. And these growth defects and vacancies lead to potential fluctuations in this band structure. And once the material is fully grown, and then if you try to actually measure it, it will turn out that the chemical potential is not always in the gap. what the chemical potential will be. It can be either in the band gap, either in the conduction band or in the valence band. Then what we have to do, as I said, we have to apply an electric field to tune the chemical potential. And when the electric field is actually tuned, try to tune into the gap, electric field tries to tune the chemical potential in the gap, then a situation can occur where you have part of the chemical potential in the gap and part of them is actually cutting these potential fluctuations, which means that even though the majority of this line is in the gap, there are small carriers over here which are trapped. And these trapped charge carriers, which contain actually bulk carriers, this is what we call as charge puddles. And these charge puddles, the dimensions of these charge puddles can be very, very tiny. There are different ways of trying to get the dimensions, and we have done it. It turns out to be about 100 nanometers. So when you have charges which are trapped into this and the dimensions very small, then due to the small dimensions, these show single electron charging events. These small charge puddles acts like a quantum dot. And once these quantum dots are close to an edge, it can interact with the quantum spin Hall channel. And now I would like to correlate this quantum dot transmission with the conductance of the quantum spin Hall channel, which we have observed. So let's consider the situation, which is the red curve. So red means higher temperature and blue means lower temperature. So the red curve, if you see, this is a normal Coulomb blockade oscillations of a quantum dot, which all of us are familiar with. In this region, where we observe a minimum, what we are plotting is the transmission through the quantum dot as a function of the occupancy of the dot. So let's suppose this region means that there is no transmission happens through the quantum dot. The dot is in the Coulomb blockaded regime. Now, when we change the occupancy of the dot through a plunger gate voltage, as the dot charges, as an electron transports through the dot, we see that there's a peak in the conductance and then again a dip, and this continues. Now, this happens at higher temperature. However, at lower temperature, something peculiar happens to these values of the quantum dots when there is odd occupancy. Now, when the quantum dot has an odd occupancy, which means that an odd number of electrons, then an electron of opposite spin from the leads can actually form a virtual state, which is known as a condo singlet with the quantum dot due to energy uncertainty, and this electron can actually transport from one end to the other. So when this happens below a characteristic temperature, which is known as the quantum. So as you keep lowering the temperature, the cross-section of this interaction keeps on increasing, and the conductance keeps on increasing, because now an electron is actually transported through the dot, even though the dot is in the Coulomb blockaded regime. And this results in an increase in the conductance of the quantum dot for odd occupancy, even when the dot is blockaded.
Also here there is the hotspot or the suitable point as in the quantum dot.
Sorry, say again.
Hotspot or the suitable point that you can tune the gate voltage.
Yes, certainly. You have a plunger gate voltage with which you can tune the occupancy of the quantum.
So kindly show the position of the hotspot in your figure.
In the figure, I'm sorry, I don't understand. So what you're asking is that for a quantum dot, whether we can change the energy levels.
Even at that point of the gate voltage, that you can find a point of the part there is no Coulomb blocking.
Yes. Can I draw it?
Of course.
Okay. No, okay. There is well.
Okay, if I understand your correction, if I understand your question. So let's suppose that these are my leads. Okay, so this is my quantum dot. These are my leads, and this is my gate, which changes the energy levels of the dot. So let's suppose this is my drain, so mu D, and let's say I have not biased it, so mu S. Everything is identical, and I have energy levels of this. Okay, so now if I apply a voltage over here, what I do is that I move the energy levels of the dot, and then as my energy level coincides with it here, then the dot is not blockaded. Yes.
Also is there.
Yes, absolutely. Same physics what happens. And now that I'm here, what can happen even when the dot is blockaded? Let's say it is not, it's not yet in this sweet spot, if you call it. So let's suppose if I have an electron with just one spin, then what can happen due to energy uncertainty? There is some energy uncertainty. Then an electron with a down spin can actually form a singlet, and then this can transfer over here. So then, due to the Kondo effect, what happens is that your conductance increases. So now, if you actually try to compare, when the quantum dot is fully blockaded, then we expect that it does not interact with the quantum spin Hall edge channels, and you observe that the conductance is quantized. Now, when we see that the quantum dot has actually a peak, it has a finite conductance, it actually interacts with the quantum spin Hall edge channels, which causes a scattering, and the conductance goes down. So if we take this picture, then you see whatever you observe here, you will actually observe a mirror image in the conductance of the quantum spin Hall edge channels, which is exactly what we observe. And in the limit of the time, so I will summarize, so finishing before time, that the fluctuations in this potential landscape in narrow gap semiconductors form charge puddles, which actually interact with the quantum spin Hall edge channels via Kondo interaction and gives rise to these observed fluctuations. Thank you.
Time for some questions.
So you have this two G4T and G2T. So I guess those are 4-terminal and 2-terminal conductors.
Yes.
So why is it like one look like twice of the? Is that expected? And
yes, it is expected. So maybe I'll come. So let's say I have a system like this. Now the bulk is insulating. So I'll talk only about the region where the bulk is insulating and where the transport is across the edges. So that means that now I have edge channels propagating in two directions depending on the spin. Now, if I have to now calculate what will be the conductance of this picture, now the conventional understanding of conductance, it will be, so the transport here is non-local. It's not a local, non-local. By non-local, I mean that even if I have a current, if I choose my current terminals, I plus and I minus like this, and try to measure voltage, which is much away from the path of the current, I will still measure a finite voltage. So in these situations, for the formalism which we use to calculate conductance is Landauer-Buttiger formalism. And if we actually use the Landauer-Buttiger formalism, in the Landauer-Buttiger formalism, the geometry of the device is very important because there is no effective distinction between current and voltage leads as such. So what we have to do is that we try to calculate the in current and out current from all the contacts. We try to calculate what is the difference in chemical potential, and then try to calculate the conductance as difference in chemical potential by current, and that will give different results. Actually, in quantum Hall, so what we see in quantum Hall, what people measure, so in quantum Hall picture, people, let's say if this is the current, and they measure, you would have always seen it is called quantum Hall effect, because it is the Hall resistance which is quantized to H over E squared. So the fact that the Hall resistance is quantized to H over E squared, that results from the Landau-Buttiger. It results only from this particular device geometry. So if someone actually measures this device into a strong magnetic field, a 2D system, this will also show a quantization of resistance to be E square over H, or multiples of, sorry, not E, it's inverse, H over E square, 1 upon N. It will show multiples, and this has nothing to do with Hall resistance. So quantum Hall effect is called Hall effect because the quantization was first seen in Hall effect, but it's purely because of the particular device geometry that was used to measure it. Otherwise, it need not necessarily be in Hall resistance.
I think we can move on in the rest of time. So now we have 15 minutes talks, and the first speaker is Sumitaba Kundu, and he's going to speak about correlated disorder in entropic crystals.
Okay. I am Sumita Kundu and working under the guidance of Dr. Abhishek Nath at Indian Academy of Science, Kolkata. And today I am going to present the topic correlated disorder in entropic crystals. So entropic crystal means crystals completely driven by the entropy. So their particles, the model system of the particles are there are only hardcore interactions within the particles. So if two particles overlap, then potential energy is infinity, otherwise zero. So actually there is no interlinear energy in the system. So particles interacted in the this crystallization is completely driven by the entropy. So all this was started when in 1957 in computer simulation, people have used hard spheres at the model system, and the system crystallizes into FC structure. And for the last 2 decades, people are using hard anisotropic polyhedra to in the pioneering work of Sharon Gotzer group in 2012. The author shown that 145 convex polyhedra of set decimals into different types of simple or complex crystal structure, plastic crystals or liquid crystals, or even disordered system. So people are using hard anisotropic polyhedra because there is the probability of different types of orientational phases in the crystal structure. So for the rest of the topic, we are interested in the orientational behavior of the particles in the crystal phase. So Quaternion is one kind of way to represent the orientation in space. So Quaternion is a different kind of number system where Q0 is the real part and Q1, Q2, Q3 are the imaginary parts. And we can measure the orientational difference by using this formula where Qi and Qj are the quaternions of a particle I and j. And two particles are exactly oriented if theta ij is equal to 0. So let's see what are the orientational phases in the crystal structure. So for the first system, you see that this is a crystal structure formed by the rhombic dodecahedron particle, and it is a crystal structure as confirmed by the diffraction pattern. And you see that all the particles are orientationally ordered, orientation in the same direction, as confirmed by the theta distribution of pairwise angles, which is a peak at around 0 degree, and the dotted distribution is for the reference, which represents the random orientations. And the next one is the plastic crystal phase, and you see that it is still a crystal phase, but the particles are oriented in the different directions. And for the if you see the pairwise angle distributions, we can see that the distribution completely coincide with the random orientations. So particles are oriented in the random directions, and one particle changes its orientation freely over the trajectory. And the next one is the crystal structure for the elongated pentagonal dipyramid shape, and it is still a crystal structure, but it seems like this system particles are disordered because it looks like this. But the pairwise angle distribution somewhere maintains some sort of pattern because it might be correlated, but we don't know the nature of the correlation or nature of the disorder. So we are interested in this crystal structure in this phase formed by the elongated pentagon dipyramid shape. And so we take the system and we calculate the absolute orientations of the particles in the orientational space. We see that there are only 4 orientations possible in the system. So based on the particle orientation, we color the particles, and you see that there are only 4 colors. So representing there are only 4 orientations possible in the system. And if we take the chunk of particles from the system, it will look like this. And if we choose the unit cell from the system, it will look like this. So is it orientationally order or disorder? What will be the notion of the order of disorder? So this fits with our notion that if in a crystal structure, if 2 particles connected by translational symmetry are orientationally ordered, then we call it orientationally ordered crystal. Because if you know the complete information of one unit cell by replicating, you can construct the whole crystal structure. But if 2 particles connected by translational symmetry is not orientationally ordered, so we call it orientationally disordered. So this notion exactly fits with this unit cell. What we get from our simulation system, that this according to our notion, this new orientationally disordered system. And what is the nature of the correlation? And we have already, I have already shown that there are only 4 orientations possible in the system. So there is a finite set of unique orientations. And if we calculate the number of particles per unit orientation, it is almost 1/4 of the total system particles. So there is equal partitioning of the system particles is happening in the system. And the one kind of pattern formed by the distribution of pairwise angles. So these 3 signatures simultaneously somewhat indicates the existence of the orientational correlation in the system. So what happens at the lower densities? And if we plot the transition matrix at the densest packing, which is 74% packing fraction, we see only the diagonal elements because the orientational motion is quenched. So if we see the particles at the unit cell level in a FCC unit cell, each of the floating particles, the orientational motion is completely quenched over the trajectory. You don't see any change of colors over the trajectory. But
can you explain the left plot once?
Okay, left plot is it says the transition matrix. It gives us the probability of hopping from one unique orientation to another unique orientation. Okay, so here you can see that the probability of hopping from 0 to 0. So there is no hopping. Particles orientational motions are completely quenched. Okay, and what happens at slightly lower densities? If we milk the system just under external pressure, just let me play the video. See that each particle is changing its orientation, but picks up only one unique orientation out of 4. Okay. As confirmed by the transition matrix plot, that each particle is hopping with one of the 4 unique orientations with equal probability. As it is confirmed by the unit cell level, each of the 14 particles at the unit cell is changing its orientation, but picks up only one unique orientation out of 4. So it means the orientational correlation is present in our system. And despite the disorder, the orientational motions are not random. Certain constant features are there across the whole system. So it indicates the strong orientational correlations. As you see that the orientational and absolute orientational distribution is almost constant within statistical range for the few packing fractions, and the orientational pairwise orientational angle distribution is almost intact. And we have checked it for multiple systems and got the same result. And can we realize more regarding the orientational correlated disorder phase? So we have checked the particle symmetry and the crystal symmetry. So we have chosen the EPD system as the model polyhedra, and the EPD has the D5H point group symmetry, particle point group symmetry. And one C5 axis is there, and it is the axis of the highest order, and height C2 are also there. So as EPD system crystallizes into FCC crystals, as the cubic crystal has the octahedral symmetry, so there are C4 axis, C3 axis also, and C2 axis. And if we see that from this unit cell figure, the blue color represents the maximum symmetric axis of the particle, and you see that the maximum symmetric axis of each particle is almost parallel to any of the C3 axis of the crystal structure. You see that for each particle, the most symmetric axis is almost parallel to any of the C3 axis of the crystal structure. And we see that alpha is the angle between the most symmetric axis of the particle and the highest order and all symmetric axis of the particle. And we see that all the particles form an angle which is less than 20 degrees with any of the C3 axis of the crystal structure, and so there is almost no population and in the C2 for the C2 axis or C4 axis. So this is not a fluke. So there might be a correlation, in the disorder phase. So you can check out our manuscript in the archive. And I want to thank my supervisor, Dr. Abhishek Das, and my immediate collaborator, Mr. Ghosh Chakraborty, and Inspire and GST. Thank you for your attention.
The past line, past one. Okay. Past one.
Is correct?
Yeah. You can also consider it for a one-dimensional spinless system. One-dimensional spinless system.
Yes.
Spinless. Then you finally do some calculation, you will find many interesting.
Okay.
You will find many interesting.
Okay.
Questions? Anyone?
Yeah. So in your system, did I understand correctly that there is positional order, but
Yes,
it
yes,
is
there is poison, all right, because it is a crystal structure.
okay. Then when you look at the distribution of the angles, and much later, towards the end, it seems like there is a cusp singularity. Is this really a singularity that you see? So when you look at where around left of 50, there is this. Seems like
Which one?
in the prop P of theta,
Okay, yes.
and just below 50, when it goes up, it seemed like some kind of singularity. Is this a general feature? Like, is this really a true singularity that you see?
Actually, we didn't check for the singularity, but it turns out to be a general feature for different polyhedra. As it is the we have checked it for different polyhedra, but this distribution, pairwise distribution is not the it is system specific. Okay, it is the as we use the EPD system for EPD for the distribution is like this. If we change the polyhedra, the distribution will be changed.
But the singularity would remain.
Probably we didn't check for it.
Thank you.
Any more questions? If not, then let's thank the speaker. The next speaker is Amit Kumar, and he's going to talk about driven shock in 3 dimensions, Euler equation versus molecular dynamics and Navier stress equation.
Hello. I am Amit Kumar. Today I'll talk about this driven shock in 3 dimensions. This work has been completed with my guide Statphys. Let me quickly describe the system that we study. Consider a system at rest with a comma sense 0 and with an external point source at the center of the system. This source injects energy isotronically and continuously into the system so that the total energy of the system increases E0 before delta. This isotropic energy injection causes sterically symmetric shock, which goes readily outward in time. With a soft front, we separate the moving particle from the rest particle. In this figure shows a snapshot of the system at time t. These red dots are the moving particles, these green dots are the rest particles, and this is the soft front. This green dot is the red dot. And across this soft front, this different thermodynamic quantities like density, velocity, temperature, and phases become discontinuous. So the sudden question arrives here, like how does this RT grow in time, and what is the spatial temporal behavior of different thermodynamic quantities? We mainly look for the 2 values of delta equal to 0 and delta equal to 1. This delta equal to 0 means like in system injects energy at equal to 0 and let the system evolve in time. This particular problem has been studied by Taylor, von Neumann, and Sedow in the realm of atomic explosion in early 1945 during World War II. This figure shows the snapshot of the Trinity explosion at different times. Taylor used this snapshot and measure this radius of soft front at different time, and he found that this radius of soft front follows the power line time like 2 before 2 by 5 in 3 dimensions. Then the question is like, what is the general form of RT in terms of delta? So if you assume that RT depends on the energy ET and ambient density rho naught and time t, then using this dimensional analysis, one can find that RT follows the power law we have it in time t like this, where d is the dimension of the system. If you put delta equal to 0 and d equal to 3, then we find this RT is as t to the power 2 by 5, which I showed in the earlier slide. And the delta equal to 1, the delta equal to 1 means like energy source is injecting energy continuously with a constant rate. For that, RT is like t to the power 3 by 5 in 3 dimensions. Here is the outline of my talk. We study the soft propagation using 3 methods. First is Euler equation, which is classic description of the soft propagation, and the second is molecular dynamics simulation, where we compare the results of Euler equation, and the third is Navier-Stokes equation. All these 3 methods are valid in are described in hydrodynamic physics, where the main mode of the energy transport is mainly happens due to the motion of the particle. If we ignore the heat conduction and viscosity term, we find that we can find the exact solution for density, velocity, temperature, and pressure. Further, if you assume that there is local conservation of mass, momentum, and energy, then their respective continuity equations give rise to give this Euler equation set of Euler equation, which is written like this. So this is the continuity of mass, this is the continuity of momentum, and this is continuity of energy. These 3 equations are given in this paper. These 3 equations are PDs and form a closed form when we specify the pressure, which is related to temperature and density through the equation of state. Since RT depends on time like this, so we can redefine the re-scaled distance like this, and re-scaled thermodynamic quantities like this, and look for solution for re-scaled re-scaled functions like r tilde, u tilde, p tilde, and p tilde, which are the function of chi only. If we put these scaling arguments in this ODEs or PDEs, then we'll get back. This PDEs get converted into ODEs, which can be solved using which can be solved exactly if we use ideal equation of state and the boundary condition at the top, which is given by this Rankine unit boundary condition. Now, from the exact solution of Euler equation in ideal gas, we find this in 3 dimensions. This thermodynamic re-scale thermodynamic profiles follow power line xi when xi tends to 0. So these exponents are independent. We find that these exponents are independent of delta. To show the same, we plot here the different the solution of Euler equation for 4 different values of delta, and we find that these exponents are not depending on the delta. Now our main aim is to compare this power law behavior using molecular dynamics simulations. Now for molecular dynamics simulation, we model for delta equal to 1. Which model is as for that model is as follows. Consider uniformly distributed hard sphere particle with at rest, which inform mass with mass unit and unit diameter, and the particles interact only through energy and momentum conserving elastic collisions. And for the driving, we implement the driving as follows: like starting from time t equal to 0, after every time interval t plus delta t, we select a random particle near the close to the origin and give it a random key. For such driving, we expect this energy to increase linearly in time, and the radius of function to increase like t to the power t by 5. These 4 plots of the 4 plots of the time evolution of the system, where we can see this spherical region denoted by red dots are increasing in time. And when we compute this radius of function and energy, we find this power law behavior which are consistent with this expectation. Now, when we compare, when we calculate these different thermodynamic quantities from the UTMD and compare with the Euler equations, solution of Euler equation using hard sphere gas considered at I equal to 10, we find that these two don't match anywhere for all the space. While in our earlier study for delta equal to 0, we saw that they were matching close to the soft front. They are not matching mainly in terms of the power law behavior. So we asked like what is the possible reason for this mismatch? we said that ignoring heat conduction could be the possible reason because it could boundary condition gradient of temperature equal to 0 near the soft center. When we added this heat conduction and viscosity term into the continuity equations, we got back to the Navier-Stokes equation, which is written like this, which are these three equations. This is the heat conduction term, and this is the driving term, and these various mu are the coefficient of viscosity, and this zeta is the coefficient of one viscosity, which is 0 for hard sphere gas, monatomic gas. When we solve these three equations using initial condition consistent with the ADMD, rho equal to rho naught, u equal to 0, t equal to 0, at time t equal to 0, and the strength of the driving like this, we find that this Navier-Stokes equation matches with the ADMD data everywhere, mainly in terms of the power law we have here. This power law behavior is obtained from the Euler equation. This power law behavior are obtained in ADMD as well as in Navier-Stokes equation. So here is the conclusion of my talk. We studied the soft propagation using three methods: Euler equation, ADMD, and Navier-Stokes equation. In Euler equation, near the soft center, this state function for the power line xi, whose exponents are independent of delta, and this Euler equation don't match anywhere for delta equal to 1. While it was matching for delta equal to 0 near the close to soft front. And when we added this heat conduction, we find that Navier-Stokes give the good description of the soft front as it matches everywhere in the space because the heat conduction to the boundary condition gradient of temperature equal to 0.
Questions?
So for delta equal to 0, I mean, as far as I remember, the Navier-Stokes term changes the solution near the core, but not in the exterior, right? But here you're saying it changes everywhere. Yeah. Here, this crossover you can see here. This is the crossover in terms. This is driving term. This is heat conduction, and this is Euler equation. This group you can see like this. If you this Euler equation depends on like R square, and this heat conduction terms depends on R. So there is a crossover in these two terms. But if you take this term, this driving term only contribute all the time. Like it dominates every time.
So is there any good reason you're taking delta equal to 0 and 1 only? Other values of delta, what you
we find this for other values of delta, we find it difficult to do EDM. So like event
modeling.
This event modeling dimension, we find different.
And if there is no more questions, then let's find the speaker. The next speaker is Ayush Chandra, and he'll be talking about condition pressure observables from generalized Lanzapie equations.
Right. So yeah, start. Right. So first of all, I would like to thank the organizers for arranging this conference and giving me an opportunity to present some of my work. And today I'll be talking about some properties of generalized Lanzapie equations and the work that is in progress with Matthias Kuka from the University of Göttingen. And since there's an ongoing work, I would very much appreciate your comments and questions. Right, so I begin with a very brief introduction, and that is, so how do you describe colloidal particles in a complex environment? So if you have a colloidal particle in a Newtonian fluid, you can describe it by a very simple equation like this, which is the usual Lanzapie equations, underdamped Lanzapie equations, that has instantaneous dissipation and fluctuating force, which is delta correlated. In experiments, what people normally do is they add polymers to this Newtonian fluid, and what that does is it basically increases the correlation time, the relaxation time of the fluid. And in many cases, these relaxation times of the fluids, they become comparable to the time scales become comparable to the time scales of relaxation of the colloid in this confinement. And in that case, what happens is the simple equation does not hold anymore, does not properly describe the entire situation anymore. And then how you modify the equation is you put some memory into the equation, and the typical way it is done is now you make the dissipation depend on not only on the instantaneous velocity but on the history of its velocities. And this is called a generalized Landau equation, and it has been successfully used to describe many many observations and phenomena of phasors in viscoelastic paths, which include some of these examples like shear thinning and enhancement of radial crossing rates, etc. Right. So there are many ways one can derive a generalized Landau equation, starting from Caldera-Leggett complete Hamiltonian picture. Today, what I'll talk about is a Bach particle model, where it's a very simple model where you have two particles, and each have their own overdamped Landau dynamics, and they're interacting via this interaction potential, which is denoted by V. And what you can do in this case is you can write down a linear Landau equation using the Zorn-Zigmori projection operator formalism. And if you take averages of these noise for in proper ensembles, which is the equilibrium ensemble, you will see that this equation follows the fluctuation dissipation relation of the second time, and this is the usual form. And this I show this ensemble here is because now so the ensemble you average this over is basically the equilibrium ensemble of the system and the Bach particle condition on where it is at the initial time. And if you don't do this, and if you just take the equilibrium Bach ensemble, you would get an additional term which corresponds to the transients. Okay, so now you have a little. So right now, I'll just talk briefly about my observables of interest here. So firstly, I will discuss something like a mean conditional displacement. So what does that mean? Suppose you have such a particle Bach model, and you have multiple cameras, for example, say, and each time the tracer particle goes to a point x0, you turn on the camera and you start recording a trajectory. And then you get a series of these colored trajectories, and what you do is you average them, average all of these trajectories, and you get something like a black line. So basically, it measures if by spontaneous fluctuations, if fluctuation goes to a point x0, how does it decay in time? And then there's a usual position autocorrelation, which just says how points in the stationary state are correlated. And the third one is something which I call the pin relaxation. It is something, so you have again the tracer Bach system, and what you do is now you take the tracer and you take it to some point x0, you pin it there, you allow the Bach to equilibrate, and then you remove the pinning and you turn on the camera at the same time. And then again, you get a series of trajectories, and then you average over them and you look at how it decays. Right. And coming back again.
Sorry, quick question.
Yes.
I didn't understand how you define x0 in the second case. The first case, you actually say you pick a point x0, and so
right.
Here, x0 is also something you're averaging over. So
in the second case, autocorrelation. So this is just because, so I do this divide by x0 squared. This is simply because I want the initial point to be 0, initial point to be 1. So this is the stationary state.
You're just dividing by the variance of x.
Right.
All right. The stationary state.
Right. So I would compare all of these, and so I divide all of them by x0, so that all of them begin at 1. Right. Coming back to the linear Landau equation. So if you have the expression, if you have the linear Landau equation, it has a simple solution of this form. The general solution, of course, finding the gamma and r, these are the difficult tasks. This is the formal solution once you have a generalized, linear generalized Landau equation. And from the structure, you can see you can now do these averages, and you can pretty easily guess that in equilibrium, I mean, when the linear Landau equation is supposed to be valid, all the three curves, the MCD, AC autocorrelation, and the PR pin relaxation, they would all be the same. And moreover, even without the knowledge of linear Langevin equations, in the equilibrium, you can say that, so in equilibrium, you know that the joint position distribution evolves by a Fokker-Planck equation of something like this, where L is your Fokker-Planck operator, and both the pin relaxation and the mean conditional displacement encodes an event which basically is a solution of this Fokker-Planck equation with the initial condition this. So this guy is stationed, the tracer is stationed at x0, and the path particle has equilibrated about it. And so in equilibrium, MCD and the pin relaxation is supposed to be the same. Right. So what do we see from simulation? So take this to study this. We take this random combinatorial interaction potential, which is again a very celebrated interaction potential that is used in viscoelastic systems. And if we do, if we look at these averaged quantities in equilibrium, we see that well, it's a good agreement and all of them overlap, even in this nonlinear interaction case. But what happens is if you pin the system very far away from the center of the trap, you will see that there is quite a strong dependence on x0, which the linear Langevin equation definitely does not predict. And since there is this strong dependence on x0, then you would obviously say that the mean conditional displacement and the autocorrelation are not same even in equilibrium. And then the obvious conclusion is that the linear Langevin equation that we wrote does not correctly describe the MCD or the pin relaxation. So this is kind of one of the statements for my talk today. And now I would move to non-equilibrium. And what is the simplest way to go to realize non-equilibrium in such a setting? Oh, okay. What is the simplest way is you now make the two temperatures different, the tracer and the path particles to have different temperatures. And to start with, I would just start with a very simple interaction potential with harmonic potential, where you can write an exact Langevin equation. And you see there is an extra term in blue here, which I haven't dropped. So in the equilibrium case, one could drop it if one takes that proper ensemble, which I showed you. And here, since it's non-equilibrium, you probably don't know how the distribution would look. But even the harmonic coupling, you exactly know because of the linear equations and the Gaussian white noises. You know what the solution of what the joint probability distribution is, and you can calculate this exact conditional distribution ensemble which you would average over. And you see that this term effectively has a finite mean, and you cannot drop it. And so the particle, if the particle is at T0, which is already the stationary state, then the relaxation would follow an equation which has this additional term. And of course, then the conclusion is that the MCD and the pin relaxation would be different. So the MCD would definitely have this term, and the pin relaxation won't have this term. And then we measure this, and this is exactly the measure of the additional term, and the difference between the MCD and the pin relaxation then characterizes the difference due to this non-equilibrium. And in general, the average MCD has, so these are the structures for these three quantities I predicted. And you see in PR, this extra term with non-equilibriumness does not appear. But and these appear like this in the MCD and the autocorrelation. And from here, it's clear that only for linear fx0 would you see that the MCD and the autocorrelations are same. And in the linear harmonic model, they are, of course, fx0, as I showed, is linear in x0, and that's why you see the pinning and the MCD follow the same curve. Sorry, the pinning, the MCD and the autocorrelations follow the same curve, while the pinning is something different. Right, and then if you do this again, the same thing with the parallel combination potential, interaction potential. The difference you would now see is now again now the autocorrelations and the MCD are also different because fx0 now in this case is typically a nonlinear function in x0. Okay, and right. So now a different kind of non-equilibrium which we had heard in the first session is now the path particle is driven by not another different temperature noise, but an active fluctuation. So the easiest form of such a fluctuation would be a one-dimensional non-ensemble particle, which either goes in, which is basically ft is a Markov jump process with states ±1 and oscillating between and hopping between each other at rate alpha by 2, and then it has these kinds of correlations. And what typically happens here, differently compared to an common non-equilibrium, is that here, when you look at this quantity in a harmonic coupling, when you look at this quantity, you see that it is something which is nonlinear in x naught. So basically, that's one component of fx naught t, which I showed. And then there is another thing which there is a GT, which is the integrated noise here that came while deriving this equation, and this GT also now has a non-linear. So basically, GT for a particular value of x naught. So GT has a specific value. So also, then this term corresponds to. So now your fx naught is two terms. One is due to the position, relative distance of the tracer and the bar, and the other is due to this non-Markovian noise of the bar particle. And here, interestingly, what you see that again, of course, MCD and the pin relaxation would be different. But here you also see the MCD has non-monotonicity. So it first increase. So if you look at a point, it can first increase and then decrease. And again, all the three quantities are different. Right. And okay, so basically, I'll stop maybe. You also see this what happens for a nonlinear coupling. Again, the three quantities are different. And in addition, here you see some oscillations, which usually these oscillations people see in underdamped systems, but then we see here also in an overdamped system. And this is basically the summary, where the conclusions mainly are linear algebra equation does not describe the average MCD and pin relaxation correctly. And this difference between pin relaxation and the MC mean conditional displacement basically can serve as a marker for non-equilibriumness, and the functional form of fx naught t determines if the MCD and the autocorrelations are same. Okay, so I'll stop here.
The potential form that's guides potential can kindly accuracy. So how the lattice manifests in your calculation?
How the
lattice. Huh? Then I have no question.
I have a question. If suppose I give you a trajectory, a fairly long one, but don't really know what the underlying model is, then is it possible to extract the properties of noise just from the trajectories?
Properties of noise?
Yeah, I mean, what sort of correlation there are, those sort of things.
No, but what I say here is now you can say if the underlying dynamics is equilibrium or non-equilibrium. That's
So I was thinking, without considering bath particles separately, you consider a model like viscoelastic model of, let's say, Jeffries and stuff like that. Whether this type of MCD and PNIC for non-equilibrium case that done?
I haven't seen that, but probably if it's for the simplest model of two things interacting by a harmonic spring is different, then it should be different. I mean, that's what I think. But yeah, we can discuss it.
Okay.
I have a very rather simple question which I missed in your. So is the stationary state is time translationally invariant for your problem? Or
Yes.
Can I see? How do I see it from that stationary equation? When you wrote down the equation for x dot integral of x dot and so I mean, even in the generalized Lanfra equation, stationary state, like that equation on the right on the blue, just in the blue, yeah, right? Is a stationary state equation? Is it the right one on the blue?
Yes.
So how do I see that it is?
So if you calculate the two-time position autocorrelation, here you find it's just a function of t minus t prime.
And so you could go for even for x dot as well. Because if it is time translationally invariant, other measures will also be time translationally invariant.
Right.
So if I calculate x dot t, x dot prime,
right,
it would be a function of t minus t prime, and that would be evident from this formula.
Yeah, I mean, so basically, if your if you have a, I mean, x dot x naught x dot t prime, you can also probably get by taking two derivatives of your two-point position of the correlation.
Just take this equation, and it's from this equation, it is not obvious to me, but maybe it's what you it's probably
Maybe we
come out.
can-
Yeah, sure.
Let's send the speakers. So the missing speaker has been found. So, let me introduce Shudip Mukherjee, and he is going to talk about noise cross correlations can induce instabilities in couple-driven models.
Hello everyone. Today I'm going to discuss how noise correlation can induce instabilities in couple-driven models. Let us start with 1D Bartlett equation. It's a very well-known equation. It's probably one of the simplest diffusion-driven decisive system. This is our Bartlett equation in one dimension. But this is the Bartlett velocity field. You can see from the if I transform x prime as x plus v naught t, v prime as v plus v naught, and t prime to t, and del del t prime transform like this, this equation of motion remains invariant. Such invariance is actually called Galilean invariance, which is very evident. This noise mentioned here is conserved noise. There is noise statistics. We can define the correlation function of V in this form. This scales as r to the power 2 pi with some scaling function. Pi is the roughness exponent and Z is the dynamic exponent. Due to the Galilean invariance and the fluctuation distribution theorem, the exponents of correlation, these exponents are known in one way exactly, which is chi equal to minus half and Z equal to 3 by 2. Now I come to our model. We propose a 1D couple-driven model with two dynamical fields. One is V and is B. V, you can see it clearly follows the 1D Bartlett equation, whereas B follows this equation. From the equation of motion, you can see V is autonomous, which is independent of B, but B is affected by the Bartlett velocity field V. Depending on the relative sign of the nonlinear coupling constants, lambda 1 and lambda 2, we can have three distinct cases. If the product of the lambda and lambda 2 is greater than 0, we call it advection. If we have lambda 1, lambda 2 product is negative, we call it anti-advection. And if we set lambda 1 equal to 0, then there will be no self-advection of these FB and FB noises are again conserved. If we check the Galilean invariance of the model, that means we transform the equation following this transformation, then we can see this equation of motion remain invariant under the Galilean transformation only if we have lambda 1 equal to lambda 2. That means our model is Galilean invariant if only have lambda 1 equal to lambda 2. Our model is a good model for the passive sliders on fluctuating surface. What it happens that in a fluctuating surface, particles are living and they move from valley to hill and hill to valley, following some dynamical rules. The surface fluctuation can be described by the field V in our model, and the slider density can be described by the field D in our model. These models are very well discussed in these references. As I mentioned, both V and both the noise in the V and the B equation are conserved. Here is the noise statistics. Here is the structure of the correlation functions. Again, this is the same scaling, but we defined exponent. As I mentioned, for 1D, we have exactly chi B and chi ZB. And even for the B of the field B, if we consider lambda and lambda 2 greater than 0, then the values of the exponent are already reported in the paper mentioned Rosal and Carter, where chi equal to -1/4 and Z equal to 3 by 2. Now I come back to our model again. What we do, we introduce noise cross correlation. The noise correlation statistics are determined by the symmetries of the field. So first I discuss one symmetry of our model. If we see the equation of our motion, this equation of motion remains invariant under the transformation x to minus x, v to minus v, and v to v. That means V is a odd parity field, whereas V is an even parity field. So their noise pollution must be odd. As a consequence of that, its Fourier transform must be purely imaginary and odd function of K. That is why I choose this form of noise cross relation in our system. Third form is also considered in this reference. Now the question is, the noise what is introduced, does it affect the steady state? First I consider the field V, as V is autonomous, we can expect its exponents even same even if it introduce noise cross relation. But to find chi B and ZB and effect of noise correlation, we use renormalization group technique. And we discussed three cases. In case one, lambda greater than 0, and the other case lambda less than 0, and the final case we said lambda 1 equal to 0. First, I discussed the lambda greater than 6. That means the nonlinear couplings are the same sign. For the Argentine analysis, we define these parameters D, E, psi, and phi, and here is the flow equation of psi and phi. At the RG fixed point, we get psi star equal to 1. That means we get lambda 1 if star equal to lambda 2 star. This is very interesting that even if star different lambda or lambda 2, of course they have same sign, but eventually in the long wavelength limit they become effectively equal. And it essentially implies the expression of Galilean invariance. As I mentioned, our model is Galilean invariant only if we have lambda 1 equal to lambda 2. That means even have a microscopically different lambda or lambda 2, but in the long wavelength limit we get the Galilean invariance. At the RG fixed point, we have P star equal to 1 and B star equal to 2. From the arguments, we get several fixed points. One fixed point is at the origin, which is unstable along the direction of psi, but stable along the direction of phi. At this fixed point, we get the linear exponents of V, that means chi equal to minus r and z equal to 2.
Excuse me.
Yeah.
Which RT that you have done?
Wilson technique.
Okay. I and psi are the field or the cup.
What?
I and psi.
These are renormalized and don't you have the redefined couplings. Okay. So we have another stable fixed point, unstable fixed point. It is this, which is stable fixed point, which is at psi equal to 1 and phi equal to 0. At this fixed point, we get the noise relation irrelevant because you can see at this fixed point phi equal to 0. And what is phi? If I see the definition of the phi is actually d cross squared by dv by dt. That means that the noise correlation amplitude becomes 0. That means it is completely ineffective at this fixed point. And we get the exponent chi equal to minus 1/4 and z equals to 3 by 2. We have another unstable fixed point, which is at psi equal to 1 and phi equal to 3 by 2. At this fixed point, we have chi equal to minus 1 and z equal to 3 by 2. The existence of this unstable fixed point makes the physics very interesting, because you can see the phi, which can be tuned by varying the amplitude of d cross, that is the amplitude and noise cross correlation. If we choose the initial value of phi such that it is below 3 by 2, then the system eventually flows to a state where we have no cross flow. But if we start with the initial value of phi which is greater than 3 by 2, we should eventually reach a state which is, of course, part of it is inaccessible, but there will be certainly the effect of noise cross correlation. So this thing makes the physics very interesting in this case, lambda 1 lambda 2 greater than 0. The RG4 background suggests there must be a strong coupling fixed point. Another fixed point is, of course, automatically not accessible. Now I consider second case where lambda 1 lambda 2 product is 0. The only fixed point we have, and it's also stable, it is at the origin, that is phi and psi both 0. You can see as phi becomes 0 in this case, so we do not have any effect on noise cross correlation. And we can also see that psi also becomes 0. That means if lambda 2 becomes 0, that means the V field actually decouples from the field V. And at this fixed point, we get the linear exponent chi equal to minus half and z equal to 2. Now it consider final case where lambda 1 equal to 0. If you say lambda 1 equal to 0, it is very evident that the equation of motion of V become linear. If we consider as a V as a surface fluctuation, then the corresponding surface will be Edward-Wilkinson surface. Now we define a new coupling, G tilde, and this is the equation of G tilde and phi. And at the RG fixed point, P star equal to 3. Similar to the case 1, here again we get a unstable fixed point and we get a stable fixed point and an unstable fixed point. At the stable fixed point, where G tilde equal to 8 and phi equal to 0, we have chi equal to -16 and z equal to 2. It is very much evident that at this fixed point, the noise correlation is irrelevant. And at the unstable fixed point, which is at g tilde equal to 8 and phi equal to 4/3, and chi equal to minus, we get chi equal to -half and z equal to 2. Again, like the case 1, if we start with initial value I greater than less than 4/3, then we eventually reach this steady state where the noise correlation is completely irrelevant. And if we start with the initial value of 5, which is greater than the 4/3, then we eventually reach a state which is of course automatically not accessible, but still we have that effect of noise correlation. Again, from the RG flow diagram, we can say there should be another strong coupling fixed point. So here is the summary and discussion of our model. So what we are studying the effect of noise correlation in a 1D coupled driven model, which was originally proposed for the passive fiber problem. One of the field V, which is autonomous in our case, and another field which follows actually 1D Burgers equation, and the second field B is affected by the Burgers field. By doing RG analysis, what we find, depending on the mutual coupling of the two fields, the noise correlation can destabilize the steady state. In general, we can say the noise correlation affect a driven system with many variables, rather in a very drastic way. It can lead to instabilities and ultimately create a new steady state or drifting properties. Finally, I'd like to thank ECRB DST for financial support of this project through TR scheme as a reference of my paper. Thank you.
Where is your stability matrix? Kindly show me your.
Oh, I haven't write it here, but we talk about linear stability analysis.
Only linear.
Yeah.
Okay. There is that marginal fixed point.
What?
Marginal fixed point. Marginal.
Yeah. This is the marginal friction. You can. Yeah. This is marginal and in the direction of phi, but unstable in the direction of g.
Okay. We try to come to me. I will say you something.
Okay.
Questions?
So is it possible to make some comments about the nature of scaling in the strong coupling fixed point?
That means you are talking about the strong coupling fixed point is not particularly inaccessible.
Yes.
Yeah, that can be exactly predicted from the mode coupling theory, which I haven't done it here. But if you see the variation of the roughness exponent, it gets decreased if you move from this direction. So if we go to the into that strong coupling fixed point, the roughness exponent will be less than you have this fixed point and this fixed point. So we can expect a smooth phase is actually smoother than the smooth phase what we have for the without cross correlation. That we only thing we can say about it.
So even noise cross correlation can make it smoother.
Yes, it often make it smoother, and because that the value of the roughness point here is greater than the roughness point here, so we can expect that roughness point will be less from this fixed point. So you can expect a smoother phase if we introduce noise cross correlation.
Yeah, can you go back to your starting equations of motion? I try to figure out what might be a good physical realization of this. Because I noticed that in your model, the linear couplings between B and B are absent, right?
Yeah.
So this is a lot like the Ertash-Kardar drifting lines model, right? Is that right?
It's very much a passive sliders model. KPZ. This is a 1D KPZ.
The first one is not, but I'm trying to figure out. So, in any of these models, what would be a plausible origin of the cross coupling? And your model clearly has a phase transition. What you're showing there is that you can tune. Was it phi? I think
phi.
Yeah, and there's some control parameter that will take you
from a state where you have a
super rough phase about which you know nothing, or from some strong coupling phase about which you don't know that much to this other one. So I'm just trying to figure out if there's some good physical system in which this can be realized.
But if you realize that Kevin system greater than equal to 2, we have something kind of
physical system.
Physical system is a passive system because the fluctuating surface can be described by the field P, and the spider density can be described by the density P. So this kind of physical system can be mapped in this model.
I'm just trying, but in the passive slider system, isn't the linear coupling generically there? Don't you have to tune something to make it zero?
Linear coupling means
you know, in the normally, I mean, the general one way of talking about this is to think of a non-zero mean for B, in which case you get a linear coupling. Or in other words, what I mean is a dx V term in the B equation, and of course a coupling to B in the V equation which you've tuned away. Yeah, so I'm just trying to figure out what would be a good experimental realization.
the noise producer we can experimentally realize at least in principle the simulation.
Yeah,
Suppose we are updating the surface with a set of random number.
I'm talking about an experiment. You can do anything in a simulation. Yeah, anyway, interesting.
Yeah. So for psi equal to 0 and for last phi, don't you expect another?
In the case 1.
Huh?
Yeah.
Yeah, psi equal to 0 and last phi. Don't you get another unstable fixed point somewhere?
Psi equal to 0 or large phi. Then if psi equal to 0, then the model is not coupled in that case. Because psi equal to 0 essentially means lambda equal to 0. Then the model gets decoupled. But we don't have any fixed point there because this is stable along the phi. So eventually, if you put psi equal to 0, the system actually flows to the state phi equal. It is stable along the phi direction. And when we get the linear exponent for the B, because you can see that lambda equal to effectively 0. So you can expect a linear exponent. We are exactly getting that case from the analytical calculus.
There are no more questions, and let's thank the speaker. Let's thank all the speakers participating. Okay, the poster session will be at the Basundhara Terrace, and you can fix your poster during the lunch session, and according to your poster numbers. And we come back here and start again at 4:30 p.m. আমি এনাকে ট্রাই করি। পরের মতো আমার কোনো কপিটাল মেলা নাহলে পেন্ডেল রূপম অফিসিয়াল বেশি টাইম লাগে
Yeah.
Supposed to start in a minute, but
everybody's coming. Tomorrow, both খারাপ লাগে মানে It's not after this. No, it's only the chapter. That's the one that I'm not so sure it's related. First, you look for the cost of technology. Actually, they find several crystals because it's all I'm taking this detective. Okay, I think
We got over it. But you got over it.
I will not call myself this anymore.
Switch from this to that.
I was always joined your work. What happened was joint project never really got off. So there was one project which was floor fluctuation theorems and one was pure biology. And then over time, the balance but I'm still in touch with this. Yesterday, the workers have the Statphys thing. This has been infamous.
Nice.
We actually wrote on Fridays and we had pictures of the stress from the old days. He's one person who was talks in the understood everything.
I believe, but it was nice because they had it's not to be used.
Yeah.
Okay, so welcome back. We got the last section of the day, and the first speaker is Nalika. She will be speaking for academics.
Okay. The mic is working.
Not clear.
No. If it turns on, no.
Just tap the mic.
All right. Yeah. Thank you. So I'd like to thank the organizers for inviting me. This is my very first statistical physics conference. And very soon you'll know why, because I don't know physics. Okay, so my lab develops statistical algorithms to learn new biology from large data sets, and that's what I'm going to talk about. And to the 2 or 3 biologists in the audience, I apologize in advance, because you're going to see the introduction from the eyes of a computer scientist about biology. Okay, so just bear with me. Okay, so this is a picture you must have seen in high school. These are 23 pairs of human chromosomes. Okay, and essentially every long molecule that you see is a long DNA molecule along with some other things. Okay, so for the purpose of this talk, we're going to consider each DNA molecule as a long sequence coming from an alphabet of ACGT. So if you look at a small portion of the 6th chromosome, this is what it will look like. Okay, it's a string of ACGT, And I said it's a small portion, right? Because it really is a small portion. If you look at the whole genome, just one set of the 23 pairs, the total DNA is about 3 billion characters and all. Okay, and so my lab is trying to understand what these characters mean and why are they called the code to lab. Okay, so the school student knows that a large part of DNA is basically accounts for genes. Right? And genes are essentially parts of the DNA, okay, that code for some molecule. Let's just take an example of protein. So you can think of DNA as a big recipe book, okay, paragraphs of which are different recipes for different proteins. Okay, and in any cell of your body, all your cells essentially have the same DNA, the same recipe book. What you have is the ability to create all these proteins, but not all proteins are going to be present in all cells. The cell makes sure that only the set of proteins that it needs is going to be present at that time. Okay, and a part of this regulation happens via DNA itself. Okay, so there are regions on the DNA, okay, which are not coding for genes. Okay, so these are shown in yellow here, which somehow control the first step. Okay, and so you can think of them as switches, but to operate the switch, you need something else because this is just yet another paragraph of the DNA. Okay, so another set of strings. So to operate that switch, you have these proteins called transcription factors, okay, which bind DNA in a sequence-specific manner. Okay, so you can see that this red protein is binding this red little piece of little signal, right? And it's really little. Okay, it might recognize this string over here. And if you have a bunch of the correct proteins in your cell at the correct location, they will turn on the gene. Okay, and if something goes wrong, you can imagine if something goes wrong here, there's a mutation, and this binding is disrupted. Okay, you might have a perfectly good gene, but that just will not be translated into a protein molecule, right? So you might have a good recipe book, but that recipe is not followed when it should. Okay, so a lot of interest now is in characterizing these regions which are called regulatory regions because they are regulating the gene. Okay, these genes come in, sorry, these regulatory regions come in many different flavors. But for today's talk, I'm going to focus, and we work on all kinds, but for today's talk, I'm going to focus on very special regulatory regions, which are called core promoters. Okay, they appear right next or right in the beginning of the gene. Okay, so they're easy to locate. The other regulatory regions can be far away and sort of have some, they act at a distance. But these promoters, core promoters, are really close to the gene. Okay, and that is the reason why these promoters have been studied for years. And so biologists have a decent understanding about what elements, what signals are present in these core promoters. Okay, and so you'll see such block diagrams which identify different signals. Again, remember signals are just ACGT. Okay, when I say signal, that's what I mean. Okay, and they're named, I don't know the full forms of all of them, but Tata is easy to explain. It's because the Tata box is in fact TATA. Okay, so the region there is TATA. Okay, so the protein that binds it is this, binds this region. And what we should also remember, and now we're going to come into some probability and stuff like that, which is that a protein doesn't always bind to this exact same signal. It allows for some variability. Okay, so the same Tata binding protein might bind to these small variations, okay, or some are not variations, or whatever. This may be the whole set of regions that it's prepared to bind. Okay, so it's not an exact match. Okay, so that is something you should remember. Okay, so what's the problem then if you know all this? Well, this is a picture that you'll see in textbooks, but unfortunately, not all these elements are present in all the promoters. And in fact, a very small fraction of promoters can be explained with these signals. So what's happening here? Is it how can we find the so far uncharacterized signals? And the other question is, how do we explain, is there a way to explain combinations? Maybe is that why we're not finding all of them? So to answer these questions, you need data. And what's happened in the last 10 years is the advances in high throughput sequencing technologies, because of which you can now measure exactly where this promoter is active. Okay, so here's what happens. If you have a gene here and it is active, let's say, what does active mean? That means the first level of control is happening, right? RNA molecules are being produced. So what you can do is measure the start of the RNA molecules, sequence them rather, go back to the genome and see how many sequences map to the mapped genome, and what you get is a peak. Okay? So for this gene in a particular cell type, you will get this peak. Another gene, maybe in the same cell type, produces a lot more RNA, you will get a bigger peak. So all this you can measure. And you can measure this in one shot. You don't have to measure per gene. You can get it globally. So what you get, so now we're coming to the data part. You get from the sequencing technologies are these peaks scattered all over the genome. Yeah? Remember, these are the chromosomes that I showed you earlier. So now if you want to analyze proteins, promoters, what you need to look at are the regions near these peaks. Right? So it makes our life simpler because we know where the promoters are, right next to the start of the gene. Okay, so if you want to look for elements at these regions, we need to look at those regions. And this is what the regions could look like if I decide to align them one below the other from the based on the start transcription beginning. So I'd just like to reiterate, if you have questions, please stop me and ask. Okay?
So the peaks are where you are finding the correct sequence.
Correct. No, not the sequence. The sequence of the sequence of the RNA molecule. There's nothing about binding here. So the experiment is telling you, oh, this RNA, that means this gene is active at this level. This other gene is active at this higher level. This gene is not active at all. So in that cell type, it's telling you that here are the regions that you need to look for, because these are the active regions. Here's where your signal might be. Yeah. The reason I have colored them, the characters in this manner, is because I will be using this kind of a representation at times. Okay, this is just a heat map. So every row is a promoter sequence. Yeah? So that's the 4 colors. Yes. And so these are all the genes that I have measured. Therefore, I should see a signal in all these regions, which I can see, right? You can see the signal clear. And one way to explain, sort of plot the signal or visualize the signal is using a logo. Okay, so a logo comes directly from Shannon's entropy. That's why the bits you see. It's really simple. So at every position, you're just calculating the probability distribution over ACTT, which is the categorical distribution at every location. Yeah, and then you are plotting the height. The height of the nucleotide is a function of the entropy. So what it's saying is that at the 10th position, you will get a T. Right? That's what this logo is saying. I mean, we usually like to, biologists usually like to visualize things, and this is a visual representation of this. Yeah, okay. So the question, that's good. So now if you plot this, you'll see that, oh, there is my data box, which I know is present. There is another signal which I can see, and that's the characteristic of my promoter sequences. Is that correct? Is this really a single model? So this is just the representative. Say, we will be using pi to denote the this matrix of probabilities. Yeah, and so given a matrix of probabilities, you can always score a new sequence. So likelihood is trivial to calculate. Okay. So, but is this single model the best way to explain these sequences? In this case, it's not, because I have created the data. It's all made up, and it comes from 3 different distributions. Okay, and all of them do contain the data box, but actually they're very different in terms of the second motif that you see or don't see. And if you rely, which is what biologists currently do, on the majority signal, you're going to miss out on this little piece that you see. Okay, so what we set about doing was to develop a method that will get back any kind of diversity or heterogeneity in the data, if there is any. Okay? And we decided to go really hard. I mean, look at really hard problems. So here, at least your elements are kind of close to each other. So we said, let's say our elements, strong signals could be anywhere, okay, within the, not necessarily close to each other. It's not really biologically relevant maybe. But let's say this is the data I generate, okay, and this is a mixed data. You really cannot see much there, right? So this is a hard problem to get back. Okay, and if you've done, especially the students out there who've done a machine learning course, you look at this and say, oh, this is just clustering. It is exactly that. Okay, so we want to get back our clusters, which we are calling architectures, okay, except we don't know what the features are that we are clustering upon. Right, so that's the critical part. Okay, so if you use something like k-means or any other mixture model, they consider all your features to be relevant for clustering, and there are many methods that will do that for you.
Could you define a cluster?
So a cluster is something that has, that's a good point. It depends on how you define it. So the idea is that clusters are going to be different from each other, essentially, at specific elements, which we don't know, specific positions which we don't know. So that's how you define a cluster. So they should be different from each other. Yeah.
So within a circle, what you have, suppose within a same cluster.
Yeah.
Then everybody has the same member at that particular.
Correct. It won't be identical because we allow for some variability, but more common in that, it's similar to each other than to the rest. Yes.
But then could appear elsewhere also, no?
They could. So basically, we need to make sure that the statistics are correct, that what you're really learning is signal and not overfitting. So that's a problem because we also don't know what K is. So you could make every promoter its own cluster, right? But we don't want to do that because the idea is that once you want a method to be general enough, so if you have a new sequence, it should look like one of the clusters. That's the idea. Any other questions?
Actually,
yes.
I don't know whether I understand your talk or not due to my limitation. But as I am understanding, you can also solve this whole thing by using some sort of toy model of the mice, constructing the matrix algebra.
So you could, are you saying you could do a PCA if you wanted? Somehow, is that what you're saying?
Matrix, matrix and
okay.
just by the current dimensionality of the matrix that you can construct with your
yes.
sequence.
So you can reduce the dimensionality. Is that what you're saying?
Okay, we talk.
We'll talk later. Yeah. So, but that brings me to the point of maybe you can use PC or something which also does dimensionality reduction, except that that reduction function is dependent on all the features. We want something that is reducing the features, or selecting the features in the space of the data, in that dimension. All right. So, so this is the problem. Okay, so we just write down what we'd like to learn. This is essentially how our research works. Yeah, we have a biological problem. We try to see what we do know from biology and how we can infer the rest. Okay, so we have our DNA sequences. Every sequence has, let's say, L nucleotides, and we're going to define a model architecture now, which contains, model, which is K clusters or architectures. And every architecture is characterized by a string of L Boolean numbers, just saying whether that position is important or not for characterizing that architecture. Yeah, so we are going to have, if it is important, for these cases, both locations are going to be important, right? Then we're going to get a 1 there, and they're going to have very specific distributions. And at the other places, when these are not important, you just score them by the rest. So there's a background, right? If you're not important, you're just like the others. If you're important, you have something specific to you. Yeah? And we also don't know the label of each sequence, right? Here, if we knew the label of every sequence, it would be trivial to find out what is special. Right? But we don't know that. It's completely, the only thing we do know are those DNA sequences, which means that these are all our parameters that we want to estimate. And what we We don't know a lot of things, but we know a little bit of probability. So we can compute the likelihood. And if we know that our data is going to be fairly noisy in the sense that many of the features are irrelevant for the clustering, we can have a prior that sort of penalizes models that are going to use a lot of important features. And that's what this exponentially decaying prior is doing. So the lambda here is telling you how much to penalize the models. It's like a regularization technique that's used often, but usually seen in supervised learning problems. The lambda is important. Okay, so I'll just show you, and that's where the contribution of the model is, right? So if you don't use a good lambda.
Lambda is like a tuning parameter.
Yes, exactly right. So if your lambda is 0, which is what a regular clustering method would do, this is what you get. So basically it starts learning sort of vague signals because they start contributing to the whole structure, right? When you increase the penalty, you see a little more structure. At some penalty, you get an almost perfect match. When you increase the penalty too much, then you're really not using the data as you should be, and you're just becoming more sparse. You don't do as well. Okay, so this is just a metric to see how well you're doing. 1 is the best, 0 is the worst, and you kind of get to well at some point. How to find the lambda and how to find the k are questions we handle by cross-validation, but we can also do it using some Bayesian approach, model selection approaches, which would be faster, which we are exploring now. But right now, I'm going to show you results from the traditional, I don't think it's traditional, but it's the cross-validation kind of approach. Okay, so to build many, learn many models, and then figure out which models does the best in terms of the left out data. Okay, all right. I can take more questions on that later. Okay, so I'll just quickly show you results of this method. So we looked at promoters of TB, it's tuberculosis, and this is from a data set where the authors grew TB in 2 different media. One is when they're happily growing with enough stuff to feed on, and one under starvation. And they measured the transcription start size. Basically, they did the exact same thing that we wanted to do on their data. They looked at the promoters and they examined what they already know, right? Bacteria have something like a tatter box. It's called a -10 motif because it comes about 10 bases upstream, right? And so they explored that motif for them. They also explored the -35 motif, which is also known to exist in bacteria. Okay, and these are their results. This is the data set. And they said that a big fraction of them contained the -10 box, which looks like this, and a large fraction had something else. And they said that the -35 motif doesn't exist. Okay, so we applied our method. We expected to see the 2 classes, but we saw a lot more. We saw 9. And it's kind of, if you just look at it, it's so they all have the -10 motif, a large fraction of them, but at differing locations. One of them also has a -35 motif. Some have additional signals that it identifies. Okay, and we were more interested in this distance. Is it just, an artifact? Maybe it's a method. The experimental approach has some noise that maybe it's all -10, approximately -10 is good enough. And so we were looking at whether there's any difference across the clusters. Is there any biological relevance to what we are finding? And we do find it. So the closer the 10 boxes to the start side, the higher is the expression value. Okay, so we get a similar picture in starvation. So remember that the TB is the same. Okay, so the DNA is not changing. What is changing are the TSS positions. And so the alignment and the genes are slightly different. Again, you see the same thing. Okay, that the closer you are to the TSS, the higher you're going to be expressed. So we looked at genes that were present in both in starvation and in exponential growth. So here's one of them. Okay, so remember the gene, the DNA does not change, right? So here's your gene, here's your start site in exponential. Yeah. In starvation, it goes back by 1. Okay, so that means it's now become closer to the to the -10 box. And the expression level also goes up during starvation. Okay, you have another gene where the opposite happens. Okay. The starvation expression level goes down, the -10 box is further away, and these are not hand cherry-picked examples. It happens throughout, in a large set of cases. That the closer, when the TSS changes, it goes in the direction of the way I said. Okay. And this is generally missed unless you are actually looking for it. Okay, I'll quickly show you another result in the fly. Okay, so here, that's just a motivating thing. Why look at fly? But I don't think this audience needs that. Okay, so this is from their paper. They said that we looked at melanogaster, that's fly, a fruit fly, and we found 4 types of promoters using experimental data. So it's the same thing, right? They find out where the gene is beginning, expressing, and so on. And they said that we know that there is a data. You remember the box I showed, the original image I showed you, where you know that there's data about this DP and so on. So they use these elements, scan them, and said that, well, there are 4 types. And we expected to get the similar results back, except that we couldn't. Whatever we did, we were not getting these results back. And then we realized that there was this sentence in the paper, in small print, pretty much. Promoter regions lacking obvious structure are not shown. Okay, so they actually showed about 2,000 of them, and there are twice as many which were just left out because they did not fit in what they wanted to show as a type. Yeah? So we used all the data because we didn't know about this, and we see a lot more structured. I'm not going to show you, but also the downstream clusters also have some interesting features. So there is some function associated with these clusters. Okay, so we call our method no promoter left behind. So yeah, for obvious reasons, because we think that a large data portion is often left out during analysis because the data doesn't always give the experimenter the results that they want. Okay, so this is kind of old work. Was done by Sneha, who's a graduate student when I was working at NCA. That's where I was before I moved to ISIL. Okay, and but we've taken this to a completely different level in the recent past, because this approach itself is something that people should, I think, be looking at more and more now. Now that you have these large data sets, you should not be looking for a common mechanism, or if you're relying on elements, you should not rely on what is already known from smaller data. Right? You should use all the data to examine the heterogeneity that you see in your experiment. So if you go back and look at the assumptions in the model, there's nothing about promoters in there, right? So you can make it work. You can apply it to any data that can be aligned and is DNA at this point. And so this is data of a GATA protein binding site. And if you just apply it, you see a lot of other signals, nearby signals automatically coming up, showing that there might be some cooperative binding. Okay? And there's nothing to stop it from being used in other ways also. So here's where we are using data from other additional biological experiments. So this is ChIP-XO data, which tells you exactly where a protein might be binding through the cuts that you get from that enzyme. And this is the data that you get. And after applying, now we have a joint distribution over using all the data that we have. Again, when you try to cluster, you see a lot more signal when we don't rely on just the known elements to scan. We've also used it, modified it to work on unaligned data. So now you have data coming with, there is no event to align it from based on. We just have multi-combinations all learned in open. That also does quite well. And now we're working on generalizing it to work on any type of data. So in your work, I'm sure you will not encounter these problems. But in your work, if you think of data that you have, which is, it's some sort of a mixed data set, you're not getting what you want, but you believe that your signal exists in there, these are approaches you can try out. And if you would like to, please get in touch with me if there's something from here you think would be of use in your own research. And thank you for listening to me.
Questions?
Yes.
One thing I didn't quite understand is when you use these L1 norms for regularization, you get these sharp edges, which is what allows you to get feature selection, right?
Yes.
So you are using an exponential function.
That's the same as one.
Oh, really? I see. Because if you just take the log, I didn't notice the. I see. Okay.
So when you put it in the probability distribution, it becomes it's a Laplacian prior.
I see. And the second question I had was, are these things that you're finding, are these real binding sites of proteins or what are they?
So for the GATA, yes, they are GATA, but they're also sort of dimers and things like that. For some of them, we know. For the promoters, we don't know. But we think for the TD case, it might just be, what is that word? The part of the polymerase, the sigma factors might be different. Because we can't tell why the distance changes just by 1 or 2 nucleotides. So there must be something that's controlling that part.
So, so is it, does it problem become any simpler if you look for the amino acid sequence instead of looking for ATCG? Because amino acids are restricted, so you have to look for a smaller setup.
So the data would be different. But the amino acid space is 20. So 20 possibilities, right? So the categorical distribution would be over 20. So that would change. But it can be adapted because there's nothing really, it doesn't need to have only 4.
Does the problem become easier or become harder?
No, I don't think it can say that it will be good. It will depend on the data. Also the question that you're solving, this is not proteins. So if you're looking at proteins, I think it would just end up getting a little harder because you won't have so many proteins at the same time. So the data is restricted. Usually you don't have proteins at that magnitude. But you would have so many characters, so many alphabet peptides. There was a question. Yeah.
Have you tried with other the same formalism with the other promoter regions apart from Tata?
Yeah. So they had non-Tata in there. These are all of them. We're not restricting. We're saying give us all. Right? So these are the only ones that have Tata. Even there you can see that there's a distance relationship with the INR also. This is the INR. And these are the DP but no Tata. So we are not restricting.
Okay.
Thank you.
Okay, let's. So next talk chemistry, and this will be after 3 minutes.
Hi everyone. So this is Chemistry today. I'm working under Dr. Shivan Kumar in ID. So my topic is biophysics related. So you might get lost somewhere, but you can look at this, remember this title, and you can find use that. So it's like correlating, providing confirmation and gene regulation by molecular simulation. So I'll be using polymer simulation models and Morse chain process to correlate the genome structure and function. So before starting, I'll give you a brief introduction about the topic. So last talk made my things easier. So if we have like eye cells, skin cells, they do have different functions, right? Eye cells can see, but and skin cells can sense the touch, but they cannot do each other's work. So they have different functions. So why is that? If you see cell nucleus, they have same genomic content, but they work differently. This is because they have different protein content, and this goes through a process called central dogma, where the genetic information which are in DNA goes through, the information is transferred to RNA through transcription process. Then the information from RNA goes to protein, and this protein decides what the function will be. So now coming to the structure, how structure is actually related to the function. So there are different regulatory elements called enhancers and promoters. So they can be very far away. They can be 1 kilo base pair to 1,000 base pair. They can be the distance can vary very much. So, but they in DNA is like coiled inside the nucleus in such a way that they form this loop kind of structures, and different structural factors like transcription factors and activators, they help them to bring close together. So now, so this long range chromatin interaction helps in the transcription process. So there have been many experiments going on to study the structure, like chromatin structure, and how they are coiled inside the nucleus, because 2 meters of DNA is coiled inside the nucleus, which has just a diameter of 6 micrometers. So now, so they have been doing this experiment since last 20 years, but in last 10 years, there have been many development in this area. So this experiment is called chromosome confirmation capture experiment, where they have like they freeze the DNA and see which of the distant parts of the DNA are they in contact or not. Which of the parts of the DNA are in contact. So these experiments have given us the idea that DNA is not in the nucleus in a non-random fashion, but in a hierarchical manner. So if we look into the nucleus, so in human cells, we have 23 pairs of genome. So we will have 23 clusters of region, which are called chromosome territories. And you can see that from this experiment, 3C experiment, or high throughput chromosome confirmation experiment, HiC experiment, we have this kind of contact map, which says that this chromosome 1 will be interact among themselves, and 2 will interact with themselves. And intrachromosome interaction is very less. And if we go to higher resolution, we will see that A and B compartments are there, which can be visible from this contact map. And if we go into higher resolution, we will see tags, and then again higher resolution, we will see loops. But we are interested in the tags because experiments have shown that this topologically associated domains or tags are functional domains of the genome, because this regulatory elements regulate each other inside one tag only. So if an answer is in this tag, A tag, it will not interact with the gene which is present in the adjacent tag. And this boundary is important because there is an insulating protein there which insulate this tags. And experiments have shown that if we delete this boundary or merge this invert this boundary region, then there will be some gene expression. So what we wanted to do, we wanted to take an example of this tags where two genes are there, which are very important for link formation. And we wanted to see how, if we change the structure, how this transcription is changing. So what we did, we take the high-C contact map and form a polymer model. So we used a bit string polymer model, and we used molecular dynamics to find a 3D structure where each pair of bead is affected by a harmonic spring, and this harmonic spring constant is proportional to the contact probability, which is taken from the experimental high-C map. Now, what we saw is that this tags, they form very distinct globular structures in 3D. And if we delete the boundary, they are now merged. If we see the contact map and 3D genome, they are merged. So what inference we can get from this structures, 3D structures? We calculated the enhancer promoter interactions and how this is changing after boundary deletion or structural deformation. So this is for one gene, this is the enhancer promoter interaction is decreasing after tag deletion, and for other gene which is in adjacent tag, it's increasing. So what we calculated all the rates of enhancer promoter binding, and we put them into we used Gillespie algorithm to find the cluster size of the promoter after a long run. And we since our kinetic model matched with the polymer model, now we can infer something from the from this kinetic model. And what we found that for SOX9 gene, after tag deletion, the gene expression level is decreasing by 20%, which is very similar to the experimental one. And for KCNJ2, it's increasing, it's getting doubled after tag deletion. So why is that? That's our input from this model, that there are certain hidden enhancers which were not recognized in the experiment. But we found that from some databases that these hidden enhancers are more active in our 3D structures. Like when we put this hidden enhancers only in our model, they get the 70% of the expression level is coming from those hidden enhancers only. So now our model can predict the functional enhancers which were not predictable from the experiment. And so these are my take-home messages, that after tag deletion, the enhancer promoter interaction is changing, and our model is suitable for predicting the functional enhancers. And as the title suggests, structure is related with the function. So you can read more about this topic from this review, and we have this paper which describes this work only. You can go through this, and these are some other references. And thank you for listening.
Are there any questions? So how exactly do you relate to the functions?
So we are calculating gene expression level from using those rates which are getting from the 3D structure. So from 3D structure, like polymer model trajectory, we are calculating the rates, finding rates and unfinding rates of regulatory elements. We are putting that in the kinetic model, and we are getting the expression level. How expression level is changing.
Okay, this you calculated against some experiment?
Yeah.
Okay. How do you define you talked about this cluster size distribution.
Yeah.
So how do you define the clusters?
Like there can be many enhancers which act on one enhancer. So how many enhancers are bind to the promoter? That's the cluster. Nice talk. So how did you decide, how do you know where the enhancers are?
We are taking from the database enhancer sequences.
But those enhancers could be from in any cell type.
Yeah.
Okay.
No, this is this example is for only one cell type, which is mouse-linked blood cells.
So the enhancers are also from that.
Yeah, yeah,
from that.
yeah.
Okay.
Okay, thank you, Shamsi. So next speaker is over. So next speaker is Shovik. And you have 15 minutes.
Okay, so good evening, everyone. So I am Souvik Sadhukan from Tata Institute of Fundamental Research, Hyderabad, and this work is done in collaboration with my collaborator Manoj, Satyam, Mateo, and John Dasgupta, me, and my PhD advisors Dr. Saroj Kumar Nandis. And this is today I'll be talking about random faster transition theory for the glassy system in confluent cell monolayer. So let's first introduce the definition of glass. So glass is very ubiquitous in nature. So like you can find glass like in window, in glass, in everywhere around us. So but the process of glass forming is very understanding the process of glass forming is very peculiar. So first when you cool a liquid, if you cool it, it will form crystal in general. But if you cool it slow enough such that it avoids the crystallization point, so you can go to a state which basically where the dynamics extremely slows down and the relaxation time of the system increases quite rapidly. So by relaxation time, I mean the time taken for the particles in the configuration to move a distance of the order of its diameter. So here, as you can see, the system more or less similar to looks like a liquid. That is, it is disorder. There is no touch of order which is developing, but the movement of the particles becomes slows down heavily, and so that's why you can if you measure the relaxation time or the viscosity of the glassy material, then you will see that the relaxation time, as you change the control parameter, which is temperature or the density. So if you change that your relaxation time or the viscosity, if you plot in log scale, and it will increase quite rapidly with a slight change in the control parameter. So now, since there is no sort of structural order that is being developed here, that's why there is no transition in thermodynamic sense. But here you can see that the relaxation time increases orders of magnitude, and that's why you can define it some sort of glass transition temperature, when after which you cannot equilibrate the system. So now this why we are interested in this glassy dynamics, because this sort of glass-like behavior has also been observed in several cell monolayer in our body and also in several organisms. Like as you can see, these are the cells from human bronchus, and one is from the normal donor, and another is from the person with asthma. And as you can see, in normal donor, the cells are moving very slowly, and this is more or less solid-like, because in solid, their movements of the molecules are very less. And in another case, where the person has asthma, if you take the cells from his lungs, then you will see that the cells are moving quite a lot like a liquid. So this is like a some sort of transition from solid-like to the fluid-like.
Now, so this sort of function you can also see when you have increased division rates, such that as the division rate increases, your cell density also increases. And if you plot the relaxation time of the system as a function of the density, so as you can see, as your density increases, your relaxation time increases. Now, so similar sort of scenario occurs when you overexpress some sort of drag in a confluent monolayer. So here confluent means that there are no gaps in between the cells. That is, the cell packing fraction is total system packing fraction is always remains 1. And here you can see if you express some sort of drag in the confluent cell monolayer, you will see that the system will be fluidized and the cells will move quite a lot. And you can also overexpress some sort of oncogenes to make the system fluidify or fluidize or solidify. And so this sort of behaviors asks us the question, why not to study the glassy properties or develop a theoretical framework for this confluent glassy system. Now we answer the question in a twofold approach. So first, we try to simulate a model that emulates the confluent cell monolayer in the experiment, and then we try to develop a theoretical framework for them. And so to develop a model for the confluent cell monolayer, we have to understand key points of the cells in a monolayer. So when the cells are in monolayer, they basically, so under some mechanical perturbation, if you give some sort of mechanical perturbation to the cells, so up to some time, let's say of the order of seconds, they try to maintain their shape with their ion channel and water pump. So, and that we have to keep in mind, and that for this shape constant, that they maintain their shape with their ion channel pumps. So that motivates us to write down a Hamiltonian or energy function for the confluent model. So one term contains the area constant term, and another term contains the perimeter constant term. Now, so what is the motivation of this area term? So since actual cells are 3D objects, as you all know, but here the height of the cell monolayer almost remains constant, and the volume also remains constant. And that basically, since height fluctuations are negligible here, so if your height fluctuates very smallly, then to maintain the constant volume, we have to change your area by some certain amount, and that will put a constant over the area. And this we can write as a 2D expression because 3D cells are incompressible. And the second term basically takes care about the two contributions from the cells. So cells, as I said, the cells in the confluent layer is always packed to each other, and the packing fraction is always equal to 1. And because of that, so you have this the perimeter term comes because you have cell adhesion energy and also the cortical tension among the cells. And that's basically the pi square and pi linear pi term, and you can combine and write down as a whole square term. So now this is how the actual cell looks like in an experiment. It is mapping that we canine kidney cells, and it is the actual living cell monolayer. And now if you simulate a model which is called the vertex model, this has been done by us. That we simulated the active vertex model which emulates the actual behavior of the confluent cell monolayer. And so you can now with this is the simplest Hamiltonian that you can write, and which can emulate the behavior of the actual cell monolayer. Now you can add some sort of activity to the system. So here in the vertex model, cells are represented as the polygons, and the equation of motion is written for the vertices. And so because the degrees of freedom are the vertices. And so now if you since the cells are in a highly viscous medium, so their Reynolds number is very low, so you can write down the Overton equation of motion. And so you can add some active boundary and particle type of activity to each of the vertices of the cell, and that goes like this, the equation of motion. And so there the two active parameters is basically this F naught and this PR, which is the rotational diffusivity and the cell propulsion speed. Now once we have the model developed, then we can do the further theory. We can write down a theory for the confluent cell monolayer for the well-established one, which is the random faster transition theory, which is well-established in particular system. But here we try to extend it for the confluent system because nobody has basically realized a theoretical framework for the confluent system before. So here, so our motivation is that we took the approach for the random faster transition theory and apply it to this confluent system. So the RFOT basically considered the cells. The system consists of different mosaic states, And these mosaics basically relaxes independently, and they also reorganize among themselves. And if you write down the free energy change of this particular mosaic, so these mosaics are imaginary lines. So now if you write down the free energy in a d-dimensional space, one term will contribute to the gain term, which is the free energy gain, and the second term is basically the surface energy mismatch term. And now if you minimize this, then you will get some sort of length scale, and by some sort of barrier crossing type of argument, you can write down you can relate the relaxation time with the length scale of the problem, and you can write down the relaxation time from the system. Now here, one thing you have to notice that the control parameter of the dynamics is the P naught, which is capital P naught from the Hamiltonian and divided by the square root of it. And here, here the other constant is taken in here by this E, and the two important term is this gamma and this configuration entropy S.
How do you define this mosaic? Like, how do you define the boundary?
So this is actually not a real line. So this is an imaginary line.
But how to draw the line?
So this is depending on the relaxation of the local relaxation of the systems. So the theory basically assumes that the system consists of different sort of mosaic states, and these states will interchange among themselves. They can either grow. This is some sort of nucleation type of argument that whenever you have nucleus formation, you just first form a small the point of nucleus, and then it grows. So that's how that same argument. But here, this instead of this in crystallization, what happens that it goes and the system fully crystallizes. But here it is basically stuck in a disordered minima. So that's why basically different mosaic state, and you have interchange between these mosaics. Now, once you have this P naught dependence term in this two denominator and the numerator, you can basically some sort of do a Taylor series approximation up to a linear order, and you can substitute it into the actual formula, and now you will get the relaxation time for the cells. This is for a passive system. Now, as I said, you can also add activity, and that will contribute to the configuration entropy term of this system. And this is the contribution due to the self-propulsion, and phi s is some sort of interaction potential, because in glassy system the system consists of several disordered energy minima. And now you can this phi s term is calculated for a one-dimensional system, and which is in a one-dimensional self-propelled particle in a harmonic trap, and this has been calculated by Saroj Kumar Nandi and Neerbo, and they have calculated it for a point particle system. But here, since, as I said, the confluent model has this layer fully covered with cells, so the DR, the rotational diffusivity that you are applying to the system, will not be the one that you will get from the if you calculate it from the simulation. So it will be different. So that will be a DR with an effective sense. And what is that DR? So now, so for the DR effective formula, to calculate that, so we consider some hypothetical scenario that. So here the cells, as I said, the cells are always packed with each other, and they can their angular orientation, their angular direction will be hindered by the other cells in the medium, because there cannot be any gap between the cells, and so that allows us to write down a Langelois equation for the angular coordinate, and with some public term and some active noise. And this active noise basically now if you calculate the phi, which is the phi correlation or the angular mean square displacement, you will get the formula for the angular mean square displacement, and from there you can define the DR effect. And you see that DR effect basically is not the actual DR like a point particle system. It is having a form like DR by kappa DR plus 1, and that means the DR that you are applying, that you will not get the DR that you calculate from the angular mean square displacement. It will be less than the run, and that if you substitute that in the relaxation time equation, you will get the relaxation time equation as this. And now, since we are interested to see the behavior of this V naught, DR, and P naught phase space, so we'll set basically we'll go to the glassy regime that we set T equal to TG, and as I said, that it's a hypothetical definition that there is no sort of transition here. But you will get you can define the transition at when the relaxation time reaches some sort of value like 10 to the power 6. You can it can vary from system to system, because there is no actual transition, there is no thermodynamic transition here. And the P naught reference value you can take as 3.81, because in actual experimental system the mean PI, that average perimeter of the cells cannot, in a confluent monolayer, cannot go beyond this value, go below this value. And now, so now if you just say put everything here, and you will get a after simplification, you will get a phase space, nice phase space equation for a confluent cell monolayer with V0, and Dr. Now, once you have this, so there has been simulated there has been a simulation data by Max P and Christian Martinez group. So what they have, they basically simulated the one of the model of confluence system, which is called self-propelled Voronoi model, and they have simulated for a for different V0, and they have this data for the defined phase space diagram, like V0 versus P0 for different DR. And what we do, so since we have the analytical formula for this phase space diagram, so what we did, we feed the data with the analytical formula that we have. Now we get the constant R, A, and B. Once we get the constant, so they have the same data for other DR as well. So what we did, we plotted the analytical equations and plotted with the same ABR that we got from the first fitting and vary BR. And as you can see, they qualitatively match with the train. And one point here is to highlight is that going from DR 20 to DR 1000, there is not that much change. And that basically ensures that concept of this DR effective, which is the DR effective that we have already derived, that it will be less in the case of the confluence system, unlike particle system. And now you can also plot the other phase diagram that they have, the simulation data, and you can see that the qualitative train is nicely matches with the analytical expression that we have. And the most important result is that the theoretical phase, the simulation phase diagram that they have in their paper can be reproduced by the analytical formula that we have derived. And as you can see, it basically exactly matches with each other, the theory and the simulation. And so, as a summary, I would like to mention here is that the confluency basically modifies the rotational diffusivity, which makes it different from a point particle system, because in point particle system, the rotational diffusivity that you are giving will be the same that if you calculate it from the simulation. But here, because of the confluency and since the layer remains always confluent, the DR that we apply to the system will not be the same DR that you will get if you calculate it. And so we have extended one of the most popular theory of glass, which is called the random fastener transition theory, and included both self-propulsion and confluence. And we compared the theory with the existing and the new simulation data. And the simulated phase diagram is matching with the theory quite nicely. And so this is the manuscript which is under preparation, and I'd like to have comments from it. And last of all, I'd like to thank the organizer for inviting me to give this talk. And
okay, so let's thank all the speakers of this session. Thank you.
For those people who are staying in the guest house, breakfast at tomorrow will be from 8 a.m. till 9:30 at Boshundara Dining Hall, where we are having all our meals. And dinner today is at the same place. It starts from 7:30.
Okay, I had a long chat.
Yes, yes.
So I think it's one of the-
You know, this is my
So this is about
that value was
each of my expect that we were doing is moving that side. So I think also we are taking it.